Okay, let's start our first session. So, welcome to the 19th Mexican School of Particles and Fields. Today, in the first session, we have the plenary talk by Professor Kenji Fukushima. He's a professor of physics at the University of Tokyo. Professor Fukushima has a very wide research interest in high energy nuclear theory, hadron physics, quantum field theory in extreme environments. He's an international expert in quantum chromodynamics, quark-hadron transition, relativistic heavy ion collisions, and quantum anomaly. Professor Fukushima has published around 120 articles with more than 9,000 citations. It's huge. And the topic today is the QCD phase diagram. Many thanks, Professor Fukushima, for accepting the invitation.
Okay, thank you very much. Thank you very much for the very kind introduction. I'm flattered. And so today I'm giving a lecture on the QCD phase diagram. And in fact, I found that this is a school of particle and fields. And so my lecture is focused on the formal aspects of a QCD phase diagram, not really the phenomenology. And so here is my talk plan. I start with a conventional picture of QCD phase diagram as a function of finite temperature and density. And so in fact, this is a sort of a phenomenological motivation is quite important, and also slightly mention the equation of state studies related to the neutrons physics. That will be, I think, more closely explained by Alexei Baryon later. And so then finally, I will briefly discuss the recent topics of quark-hadron continuity and some topological discussions. So how to distinguish quark matter from nuclear matter. This is very, very interesting topics. And then I will switch my gear to the next topics. That is the phase diagram at finite magnetic field. This is very, very interesting. And there were some confusing things. And recently, we did some interesting work, which I will introduce. And the final topics is the finite rotation. This is another very interesting topics. And these might sound a little bit academic things because I will discuss a strong magnetic field limit and also the very fast rotation limit, but they are both motivated by the heavy ion collision experiment, realistic nuclear physics experiment. But anyway, there are lots of interesting theoretical things, as I will explain later. Okay, now the first story is about the finite temperature and density. And so here is one example of conventional QCD phase diagram. Actually, in the market, there are hundreds of or thousands of different variations of QCD phase diagrams because essentially this finite density region, they are unknown. Okay, so the experimentally and theoretically, there are so many possibilities, and also the theoretical uncertainty is so huge. And so there is no QCD-based first principle calculation yet. And so there are many scenarios, and nobody knows which one should be the correct one. But anyway, so this is one of the example that I believe. And so some years ago, more than 10 years ago, I wrote a review article with Tetsuo Hatsuda. And so there are many, you see, there are many lines here or some dotted lines, etc., etc. And they represent some special kind of phase transitions. But of course, I do not have enough time to explain everything. And so only limited features of the QCD phase diagram can be explained here. But anyway, there are many complicated scenarios. Well, but to understand these physics features, there are actually two important things. One is actually the chiral restoration. That is QCD phase transition in terms of the QCD mass or dynamical mass. Actually, in QCD, it is very well known that the mass comes from the QCD interactions. And so when the temperature is small or the density is small in the QCD vacuum, the quark comes together with the interaction clouds around it, and then the bare quark mass is only a few MeV. However, the dynamical quark mass is several hundred MeV, which is QCD scale. And this scale originates from the running coupling constant. And in the running coupling constant, you see the typical QCD scale that is called the lambda QCD. So this scale itself is not gauge invariant, so this is not really observable. However, still, this is a very nice bookkeeping device to see the QCD physics, the typical scale of QCD interactions. And so all the QCD phenomena are characterized by this scale, lambda QCD, which is usually several hundred MeV. And so this dynamical mass scale is indeed of order of lambda QCD. But if the temperature is high, and so this temperature scale is again characterized by lambda QCD. So if this T is comparable to lambda QCD, the interaction becomes weak, okay, due to the asymptotic freedom. And eventually the interaction becomes too weak to keep this interaction cloud, and then the interaction cloud is gone, and then you get the bare quark, and which is almost massless. So in this sense, the mass is completely gone when the temperature is raised up. And so in this sense, this is a phase transition in terms of the mass. Okay, so this, of course, this phase transition can be characterized by symmetry because the mass is related to the chiral symmetry of QCD. That is, if the mass is 0, the left-handed quarks and right-handed quarks are completely decoupled. And the left-handed quarks have a spin and momentum anti-parallel to each other, but the right-handed quark have their parallel spin and momentum, and they do not talk to each other if the mass term is 0. But because of their dynamically generated mass, these symmetries are coupled together and broken down into the vectorial SUNF symmetry. And in this way, actually, there is an order parameter corresponding to this global symmetry breaking. And this is actually nothing but the chiral condensate Q bar Q. So this is very simple physics. And another important aspect of a QCD phase transition is deconfinement. So that is, the quarks are confined inside of hadrons, forming some color singlet. But if the inter-hadron distance become shorter and shorter, that is characterized by the temperature again. And so this interparticle distance is usually given by 1/T. And this hadron size is given by lambda QCD, which means this temperature scale become comparable to a lambda QCD. Then they start having some overlapping, and then this hadron boundary loses its clear definition, and then the quarks can hop from one hadron to another hadron, etc., etc., and then the mobility of quarks should be enhanced. And in this way, it is quite natural to expect the deconfinement of almost freely hopping quarks. And that is nothing but the deconfined matter in terms of quarks. And again, this characteristic temperature should be given by lambda QCD. And so then the question is, what should be the order parameter? To define the order parameter, let's perform the following thinking experiment. Just put a test quark inside the medium. And this test quark is static and very heavy. And then you can define the free energy associated with the presence of this test quark. And if this free energy is infinitely large, then the presence of this test quark is not allowed, which means that the vacuum is confining. But if this free energy gain is finite, then the system is in the deconfined phase. And in other words, if this F is exponentiated like this, So, but of course, inside of the exponential, some dimensionless quantity must come. And to make this quantity dimensionless, usually the temperature appears in the denominator. And so if this quantity is zero, if this energy gain is infinitely large, then this exponential becomes zero, right? And so this exponential quantity can be regarded as an order parameter for the confinement phase transition. And so if this is zero, then you can think that the system is in the confined phase. And actually, in terms of the field theoretical language, this quantity is given by the expectation value of the Wilson line, which is called the Polyakov loop. So anyway, so this is a formal definition of the order parameter. And anyway, in this way, so you can introduce two order parameters to characterize the two phase transitions, two QCD phase transitions. And in fact, if the density is zero, you can perform the lattice QCD simulation, the first principles calculation, to see the behavior of these two order parameters. And this one, this curve shows the behavior of the chiral condensate Q bar Q. So this one is, yes, this is a Q bar Q expectation value. And this one is actually the Polyakov loop. In my notation, the trace L. Okay. So this is a phi in my notation and trace L. Okay. And as you see, the Polyakov loop is almost zero when the chiral condensate is non-zero, but the chiral condensate approaches zero when the Polyakov loop takes a finite value. And in this way, the ordered phase and disordered phase, they switch to each other almost at the same temperature. So this is actually a quite non-trivial feature, but this is not very surprising because, as I told you, both phase transitions are characterized by the same scale, that is a lambda QCD. Okay? And indeed, this temperature, 150 or 200 MeV, this is very close to the lambda QCD scale. That is usually 200 MeV or so. Okay, so everything is quite natural. And but the interesting thing is that you can also get some information from experiment. Okay, so far, all the arguments are very theoretical arguments, but so these physics features are quite relevant for the realistic experiment. And in fact, this is a sort of a phase diagram investigated by the heavy ion collision experiment. So on the plane of the baryon chemical potential and the temperature, and then the question is how to identify these density and the temperature in the experiment. And what they did in experiment was very simple. That is, they measured the particle ratio, the pion and the kaon, and they measured the various yields of hadrons, the proton and lambda bar, etc., etc. And then these ratios are determined by the chemical potential and the temperature if you assume thermal distributions. Okay, the Bose distribution or Fermi Dirac distribution, and if there's such a thermally equilibrated matter is assumed, then the ratio is completely fixed by the chemical potential and the temperature. And from this fit, this is called a thermal fit, the mu and T are identified. This is how this phase diagram was drawn experimentally. But the question is, what should be the underlying physics? The underlying physics is very, very interesting. This underlying physics is actually the Hydron limiting temperature. That is a very old observation made by Hydron. That is, if you see the Meson spectrum and the Baryon spectrum, the spectrum grows exponentially with mass. So that is if you count the number of mesons and the number of baryons, or including resonances, not only their stable states, but also resonances, then if the mass becomes larger, you have more and more states, more excitations in mesons and baryons both. And then the number of particles or number of species grows exponentially. And then what happens if that is the case? And what happens is very, very non-trivial. That is, if you see the thermodynamic quantity that is usually computed from the partition function, and if you assume such an exponential behavior of the mass spectrum, then if this is convoluted with the Boltzmann distribution, that is exponential minus m, okay? And then you can perform the summation or the integration with respect to all the energy mode, right? And then you can get the pressure or the thermodynamic quantity, okay? But if you do this integration, assuming that this spectrum grows exponentially, and if this exponential rate is greater than this Boltzmann suppression factor, then this integration diverges, which means that if the temperature becomes larger and larger and larger, then the Boltzmann suppression factor is more and more suppressed, which means that this cannot overcome this exponentially growing Hydron spectrum. And eventually, the thermodynamics breaks down. And so the Hydron actually postulated that the temperature must have some limiting value. But now, his interpretation is not really correct. And this limiting temperature is nothing but the phase transition temperature. And this hadronic description should break down and can be taken over by the quark more fundamental degrees of freedom in terms of quarks and gluons. But anyway, in this way, so you can identify where the phase transition is located from the Hydron temperature. Okay, you see from this mesonic spectrum, baryonic spectrum, you can read out the mesonic Hydron temperature and the baryonic Hydron temperature. And at zero density, the mesons are the dominant degrees of freedom from which you can find that the transition temperature should be close to this mesonic Hydron temperature, while at finite density, the baryon is a more dominant component, and then you can, from the same argument with some modified Boltzmann suppression factor, including the chemical potential dependence, you can also conclude the similar expression of the transition temperature, including chemical potential dependence. And in this way, this phase diagram can be understood by these two phase transition lines. Okay, so this is actually one phenomenological or experimental way to understand the QCD phase diagram. But what is more non-trivial and more interesting is that this Hydron type description is, in fact, very nice to capture the fundamental properties of QCD thermodynamics. In fact, if you make a comparison between the lattice QCD computed thermodynamic quantities, like the internal energy and pressure, this is actually a special combination of the energy and pressure, which is called the interaction strength. But anyway, if you make such a comparison, then this Hadron resonance gas. This Hadron resonance gas means that you just assume such a non-interacting gas of hadrons. But many hadrons, like this, or the exponentially growing thousands of hadrons, mesons, and baryons. Okay, and if you assume such gas of non-interacting many species of hadrons, then you can reproduce a thermodynamic behavior. Okay, so no fitting parameter at all, but as a function of temperature, the thermodynamics, the energy, the pressure or internal energy increases corresponding to the deconfinement phase transition, at which you have more and more physical degrees of freedom, and such behavior is correctly described by the Hadron resonance gas. So this implies that non-interacting resonances is a dual description of strongly interacting quarks and gluons. This duality picture is actually very surprising. But anyway, this works very nicely if you see the lattice data. Okay, and in this way, actually, you can understand the QCD phase transition in the following way. That is, if you see the behavior of the QCD thermodynamics, the pressure usually behaves like this. And that can be computed from the first principle lattice simulation. And as a function of temperature around lambda QCD scale, you have some smooth crossover from the hadronic phase to the quark-gluon plasma. That is the plasma state in terms of quarks and gluons. But the hadron description, hadron resonance gas can reproduce a behavior up to this transitional point. But of course, breaks down, its validity is lost above some temperature. And then eventually this description should be taken over by more partonic description in terms of the perturbative QCD. But in this way, around this region, you can expect some duality. Okay, duality between the hadronic description and PQCD. This is actually the modern picture to understand the crossover behavior. This is actually very important to understand the high density behavior of QCD matter. Well, now let me come to the more interesting points. That is the deconfinement at high density. Okay, so far, my story was limited to the high temperature behavior in which the Lattice Qcd simulation is available. And so anyway, the first principle answer is given. But at high density, the Lattice Qcd is impossible. And so nobody knows the correct answer. But anyway, there are lots of non-trivial things. And one of them is that the PQCD cannot be justified naively. I mean, at high temperature, the PQCD should be the correct description because if you go to the higher and higher energy, the asymptotic freedom means that you have smaller and smaller coupling. And so the weak coupling perturbative calculation should be there, better and better approximation. However, at high density, that is not necessarily the case. One of the reasons is that the chemical potential have the direct coupling to quarks only, but not gluons, right? And so to justify the perturbative calculation, the gluons must be screened. And if you have the Debye mass that is proportional to chemical potential, the screening scenario works. And then the soft gluon is screened and only the high energetic gluons can be found. And if this is the case, the perturbative calculation is justified. However, inside of the plasma, it is known that magnetic gluons, or the transversely polarized gluons, are not screened. And the Debye mass can be seen only in the longitudinal direction of the electric sector. And so this screening scenario does not work. And so the asymptotic freedom does not guarantee the validity of the PQCD calculation. Okay. And that is actually more obvious if you take the largency limit. In QCD physics, usually people take the largency limit to simplify the theoretical argument. And 15 years ago, the Larry McLellan and Rob Pisowski found a very non-trivial feature from the largency limit of a QCD. That is, you may think that the baryons are of course color confined and color singlet object, and so the pressure should be of order 1 in the fictitious world of largency. I mean, the NC is the color number, and in real world, NC is 3. So this is of order 1. But suppose that there are so many quarks and gluons, and the color number is infinitely large. Okay, then the baryonic matter, the pressure of the baryonic matter is expected to be of order 1. But the quarks are colored objects. And so the pressure of quark is expected to be of order NC, right? But they found that if you consider the baryonic pressure, the baryons should interact very, very, very strongly. And such interaction potential gives you the pressure of order NC. And that comes from the quark exchange. If you consider the two baryons, for example, then each baryon is composed of NC quarks. And so there are actually NC combination, combinatorial factor appears from this exchange process of quark, okay, between two baryons. And so this interaction is naturally proportional to NC. And so the kinetic energy is indeed the of order 1, but the potential energy is proportional to NC. And from this interaction, the pressure of a baryonic matter is also of order NC. And so they actually propose a new picture that is even in the confined phase, the baryonic matter or nuclear matter has already some property of quark matter. Or in other words, the baryonic matter and the quark matter cannot be distinguished from the theoretical argument. That was actually their observation. And such, dual matter between a baryonic matter and the quark matter, that is called a quarkionic matter. Okay, so this funny name was given by these people, but this is nothing. So you may think that you may just say that, oh, quarkionic matter is simply baryonic matter, because this is actually the baryonic matter of order NC. Or you can say that, oh, this is quark matter because the NC scaling is just same as quark matter. Okay, so this matter is actually both baryonic matter or quark matter. Or anyway, there is no meaning to make a clear distinction between them. Okay, this is actually a funny statement, but this is actually very important to understand the correct physics. And in fact, to understand this, we propose some picture based on the quantum population, but this is a little bit complicated picture, so let me skip this. But now, so this actually is some continuity picture or indistinguishable property between nuclear matter and quark matter. This is very important to understand neutron star physics. I think that Alexei Borinen will give you a lecture about the neutron star EOS construction, but it is now a sort of established fact that the baryonic EOS, so that is this part or this part using their figure. So this is my figure and this is their figure, but you see they're almost the same structure. The pressure and the energy density, they have some behavior in their the low density region in which the hadronic matter should be the correct description, but beyond some point, the slope is changed, but smoothly changed, and then the natural interpretation is at this point you get a crossover to a quark matter, but there is no jump, or there is no first order phase transition. If you have the first order phase transition, there must be some the flat region that cannot be seen. Okay, and so even if there is some phase transition to a quark matter, there must be a smooth, the continuous transition, which is called a crossover. Okay, and so the question is how such a smooth crossover is possible, and the key notion to understand this, the smooth transitional behavior is actually the duality, or some duality between quark degrees of freedom and hadronic degrees of freedom. And in fact, this theoretical foundation was given by Thomas Schaeffer and Frank Wilczek many years ago. And this is in fact a very, very interesting story. So let me introduce this, okay, the argument. And in fact, the argument is based on the color superconducting picture. And if you go to the very high density, it is natural to expect that the quark matter must be gapped. That is because if you see the QCD interaction, the QCD is, unlike a QED interaction, QCD is a SU3 charged gate theory. And so there are many interaction channels. And there are some channels in which you can find attractive interaction. Okay. And so even without phonon, you can find naively the attractive interaction between quarks. And if you have a Fermi surface, and if you have such attractive interaction, the superconducting phase should be the ground state. Okay. And in such a way, the so-called good diquark, that is triplet diquark, forms the finite condensate. And the color flavor locked states, that is some special combination of color and flavor. Like, for example, you see the UD quark and DS quark and SU quark, they make some Cooper pair. Okay. And then make a finite condensation. So that is a color superconducting phase. But if it happens, then the interesting thing is you can never distinguish hadronic matter and quark matter. The reason is very simple. Okay. For example, if you have the baryons, baryon is actually constructed by the combination of the diquark and quark, right? The baryons are 3-quark objects, right? But as I told you, if the density is high enough, the diquark can make a finite condensation, and then this diquark can be absorbed by the condensation. Okay, this is now a part of the vacuum. Okay, and so then what is remaining is actually the quark. And so in this sense, the baryon excitation and quark excitation, they have one-to-one correspondence, right? And in such a way, you can establish one-to-one correspondence for any physical excitations, like for example, the vector in the vector channel, you can make there some one-to-one correspondence between gluons and vector mesons, or actually the pions for the pionic collective excitations. You can also establish some one-to-one correspondence in the octet excitations. Well, so this is a little bit a complicated story, but anyway, so, okay, so let me skip this and, well, okay, so, okay, this is just the, what should happen inside of the neutron star. But anyway, this is a little bit complicated story, but now, the recent development is actually, there's still a possibility to distinguish quark matter using some topological argument. This is very interesting, but this is very controversial. So there is no clear answer yet. Okay, so which means that it is very, very exciting in theory. So let me perform the following thinking experiment. Okay, if you have a bucket, okay, and so around the bottom of the bucket, you have a quark matter, and around the top of the bucket, you have the hadronic matter, okay? And then just make the rotation, okay? And what happens? Because as I said, if the density is high enough, the quark matter is gapped. And also, we know that inside of the neutron star, the hadronic matter or nuclear matter is also gapped. Making, having some finite component of a superfluidity, which means that you have a superfluid vortex, okay, in both sides. And if the continuity scenario is a correct physics, then the vortex excitation must have also the continuity, right? And this was actually investigated by us several years ago with Gordon Bem and Mark Alford and Tetsuo and Motoi and so some of my friends. And then we proposed the following scenario, based on some the theoretical calculations. In the hadronic phase, the baryon superfluid, I mean the baryon Cooper pair makes condensation, and such component makes a superfluid, supercurrent around the vortex. But inside the quark matter, they are actually restructured into 3 diquarks. And one diquark takes care of this, the circulation of the vortex. Okay, the circulation or the vortex is a topological object, and so the winding number should be conserved. Winding number is a topological number, and so it cannot be changed. And that winding number is related to the supercurrent around the vortex, and that can be actually smoothly connected by this restructuring of the degrees of freedom. So that was actually our scenario. However, immediately after our paper, the Chairman and Sen and Yaffe wrote a very, very interesting but confusing paper. They found that, in the presence of the vortex, they calculated the Wilson line expectation value. Okay, so around this vortex, the vortex inside of the Quark matter, okay, in this region, everything is actually the perturbative because the density is high enough. Okay, and so you can write down the gauge potential, and then you can write down the Wilson line expectation value perturbatively. Okay, that everything is actually calculable, and in such a way, they did the Wilson line expectation value calculation, and because this, that this diquark is a colored object, so this vortex is also colored, which means that this actually accommodates color flux tube inside. Which means that if you measure the Wilson line, then the flux is measured. That includes also some SU3 contributions. Okay, and because of that, they found that there is some funny fractional phase appears. And this fractional phase, or the Z3 phase, is related to some emergent symmetry, Z3 symmetry, which is actually the two-form higher form symmetry, two-form symmetry. But anyway, the point is that, as I told you, this fractional phase is related to the color flux tube inside of the vortex. So if the vortex is placed in the hadronic phase, there is no color flux tube because everything should be confined. And so this phase should be trivial in the hadronic phase. This means that if this phase, the calculation is correct, then you can actually distinguish the hadronic phase and Quark matter by looking at this phase, right? So they say that, there should be an interface between two phases, and this must be the order parameter, okay? And so actually there is no conclusive argument yet. And in fact, so these people, Hirono and Tanizaki, actually discussed some counter argument. And anyway, so this is a very mathematical paper, but if you are interested, this paper and this paper, so you can just read them. And there are some following discussions by Chairman. But anyway, this is very interesting. And so this topological probe may work to distinguish two phases, or there are some other scenarios in which the phase could be somehow screened out, or I don't know. But anyway, so this is some interesting, unsolved problem in QCD. Okay, now let me come to my next topics. That is a magnetic field. Okay, so maybe I spent too much time in the first topics, but anyway, the magnetic field is also quite interesting. Okay, the typical magnetic scale is like this: the neutron star or magnetar. Magnetar is a special kind of a neutron star. And also the interior of the magnetar, you can find some very strong magnetic field because the magnetic flux is squeezed. But still, this is only comparable to the QCD scale, 100 MeV. But if you see the heavy ion collision experiment, you can expect even stronger magnetic field. You see, this is charged nuclei. They are charged nuclei, and they collide. And so they can produce their very strong magnetic field. And because they travel almost at the speed of light, so this generated magnetic strength is very, very, very high. And this is in fact the 1,000 times larger than the surface magnetic field of magnetar. Okay, so well, they are comparable to this scale. Okay, or even larger than this, the GB scale. Okay, and so there must be some QCD effect coming from the magnetic field. Then what should happen? That is a question. And at the same time, you can expect very, very large angular momentum. But this is actually, I will come to this point later. Okay. Now, what should be expected? So actually, if you see the fermion spectrum, if the magnetic field is strong, the quantum mechanics tells you that the random quantization is expected. And if you have the spin, and then the random quantization pattern is very interesting. That is, only one spin state is favored, and the lowest, the zero mode, the zero gap state appears only in one spin state. That is quite natural, right? If the magnetic field is applied, and then the spin parallel state is more favored rather than spin anti-parallel state. Okay, so only one spin state can be found in the lowest energy state. Okay, and then the thermodynamic quantity is modified in this way. That is, phase space integration is replaced by the sum over the random levels. And if the magnetic field is very, very, very large, then this gap, this spacing between two levels, this becomes larger and larger, and eventually you can forget about this gap state. And so you can just look at this lowest energy state, okay, as a first approximation. This is called the lowest random level approximation. And then you can actually understand many interesting phenomena in this way. Okay, if the magnetic field is very strong, effectively, the system is actually reduced into the 1+1 dimensional. This is because the phase space integration is replaced by this, and then only this phase space integration along the magnetic direction. This remains intact, but the transverse direction is replaced by the magnetic motion. And if the magnetic field is very strong, only the zero mode remains. And so this is simply the one-dimensional system, but the phase space factor is actually appears, and that is this EB over 2 pi. And so approximately you can get the answer by this, a very simple calculation. And from this, you can understand the many interesting phenomena like magnetic catalysis, magnetic chiral magnetic effect, etc., etc. And in this talk, I will talk about the magnetic catalysis only. And what is magnetic catalysis? This is actually the phenomenon that the chiral condensate is increased by the effect of the magnetic field. This is actually the specific cartoon of a Q bar Q. As I told you, Q bar Q is the order parameter for the chiral restoration, chiral phase transition. And this value is increased if you impose stronger and stronger magnetic field. And so this you can understand from this 1+1 dimensional nature, or you can alternatively understand this in the following way. That is, if magnetic field is applied, or this, the Q bar Q is the spin singlet, sorry, the spin zero, total angular momentum zero state. Okay, this is a scalar condensate, scalar quantity, and to form the scalar, the orbital angular momentum must be 1, and the spin must be 1 to make the total angular momentum 0. Okay. This is necessary because otherwise you get the pseudoscalar. Okay, the particle and the antiparticle have opposite proper parity, right? And so the relative orbital angular momentum must be 1 to compensate for this, the opposite proper parity. And so the L equal 1, the S equal 1 should make the J equal 0. This means that the spin should be a triplet, okay, not singlet. And this triplet state is more favored by the presence of the magnetic field. And in this way, this condensate is enhanced. This is intuitive explanation, okay. But what was found by the Lattice Qcd simulation was surprising, very surprising. That is, you see this is a chiral condensate Q bar Q as a function of the magnetic field and the temperature, okay? And you see, so this is a magnetic direction. And at zero temperature or low temperature, if the temperature is low enough, you see this chiral condensate increases, okay, as a function of the magnetic field. This is consistent with a magnetic catalysis, okay? But what is not trivial is the transition temperature is pushed down if the magnetic field is stronger. You see, if the magnetic field is zero, then the chiral condensate melts around this temperature 100, 500 MeV, that is of order lambda QCD. But you see, if the magnetic field is very large, then the transition temperature is pushed down. Okay, this is around, I don't know, 140 or 130 MeV, and so pushed down. So this is very surprising because people usually understand that chiral symmetry is spontaneously broken by the BCS scenario. And according to the BCS theory, the transition temperature should be proportional to the gap at zero temperature. The gap at zero temperature is this, okay? And even though the gap at zero temperature is increased, the transition temperature is decreased. So this is very unconventional, and this is far from understandable from BCS theory. So this is a challenge to a number theory, I must say, okay? And so many people actually discuss or propose theoretical scenarios. But in fact, there is one very simple way to understand this. As I told you, the Hadron resonance gas is a very convenient description to understand the QCD phase transition, okay? And as I told you, this is a very simple model, but this can reproduce the thermodynamic properties. And by looking at such, increasing behavior of the energy density, you can read out where the phase transition should happen. And in this way, actually, you can put this very simple model in an environment at finite magnetic field, and then you can actually see the modification in the thermodynamic quantities, and that we did. And we found that indeed, such transitional behavior can be found at even smaller temperature. And this is very consistent with this picture, okay? And so, in fact, this is surprisingly, the simple description, but still, this can explain such a non-trivial phenomena. So this is actually my favorite model in this way. And okay, so this is a little bit complicated story, and I think that my time is running out, and so let me skip this part. So this is very interesting, but this, the Skyrmion discussion, and the topological winding, etc. But let me skip this. This is a bit too much, complicated thing. And now, using my okay, I still have a few minutes, I think, and now let me explain how interesting the rotating fermionic matter is. Okay, so this is really interesting because you can find the very serious controversy here. And the controversy means, theoretically, the theoretical challenge, right? Well, and so this is some very simple formulation of how to describe rotating fermions. And after some algebra, you can find that the Hamiltonian can be shifted by the this term, extra term, in the presence of the rotation. This is simply the shift by the product of the rotation velocity omega times the angular momentum j. And so this looks like the finite density, right? Because if you have the finite density, you have the energy shift by the chemical potential minus mu. And instead of the chemical potential, you have this shift, the angular velocity times angular momentum. Okay, so in this sense, actually, the effect of the angular velocity is very similar to the finite density. And that is true if you see the phase diagram. Well, yeah, so this is some experimental motivation. In fact, this rotation is confirmed by some heavy ion collision experiment. But anyway, this is, I skipped this. So now you see this is some calculation by my friend, Jinpeng Liao, and he's a student. And so the phase diagram looks very similar to the finite density phase diagram. Okay, instead of the chemical potential, now you have the angular velocity. Okay, and then the topology of the phase diagram is completely the same. And this can be easily understood from the analogy between the chemical potential and the angular velocity omega from the expression I showed. And in this way, actually, if you consider, for example, the chiral condensate as a function of the rotation velocity, this omega is actually nothing but the small omega. This is actually a bit notation is different, but and then you see the melting behavior of the chiral condensate if rotation velocity becomes larger and larger. Okay, so the chiral phase transition is expected, but what is very, very non-trivial is what happens in the deconfinement sector. Okay, so the Victor Braguta actually reported the Lattice Qcd simulation. I must say that the Lattice Qcd is very non-trivial. Okay, in the case of the magnetic field, the Lattice Qcd has no problem. There is no sign problem. And the strong magnetic field can be studied by the first principle Lattice Qcd simulation. But rotation is a different story. The rotation is very similar to density, as I told you. And at finite density, the lattice simulation is impossible. And by the same reason, the finite rotation simulation is impossible. But they actually introduced the imaginary rotation. Okay, the omega was replaced by the imaginary omega. Okay, and in this way, so the sign problem was removed by hand. And if you consider, if you find, for example, the this dependence, the omega I squared, then this is just replaced by minus omega squared. Okay, so this is a trick. And in this way, so they measure the Polyakov loop as a function of the radial distance, okay, the rotating system. And so this x is actually the radial distance from the center of the rotating matter, okay? You consider this. And now x equals 0 is the center of the rotating matter. And so this shows the radial distance from the center of the rotating matter. And you see the Polyakov loop. Okay, these red ones, red data show the Polyakov loop values above deconfinement temperature. So this is deconfined matter. Okay, but the important fact is, so here the left one is a non-rotating situation, and the right one shows the rotating situation. Okay, and you see this change here. Okay, here and here. You know, the Polyakov loop is slightly pushed up. You see? And as I told you, this is imaginary rotation, which means that this behavior or this rotation angular, the rotation velocity dependence, the sign should be flipped, which means that if the x becomes larger and larger, then the Polyakov loop should be pushed down for the physical rotation velocity, okay? The behavior is opposite, okay? And smaller Polyakov loop means more confinement, right? Zero Polyakov loop means a confinement. And so the smaller means the system approaches more confining situation. So they found that if the matter is rotated, the confinement is somehow favored. But this is very strange, okay? Because you see, as I showed here, the rotation is similar to the deconfinement, and usually at higher and higher density, the chiral symmetry is restored. Okay, and when the chiral symmetry is restored, it is natural to expect deconfined matter. But this statement is completely opposite. Okay, they say that the confinement, you have more confinement at larger velocity or higher density, okay, the corresponding density. And so motivated by this lattice simulation, we did the Hadron resonance gas simulation, the calculation. the Hadron resonance gas is such a useful description. I showed the strength of this model to explain inverse magnetic catalysis, right? The inverse magnetic catalysis is such a non-trivial phenomenon, but very nicely reproduced and completely consistent with lattice. But what we found was, if the rotation velocity is increased, then the deconfinement phase transition temperature is pushed down, okay? So this means that the system should go to a more and more deconfined matter. So this is completely opposite to the lattice observation, okay? And so I have no idea how to explain the lattice data. And the lattice data is very strange because, in fact, from this simple calculation, you can see that the pressure is position dependent. You see the Polyakov loop is position dependent in this way. And this position dependence can be understood in the following way. That is, okay, well, okay. So here, this is a schematic picture of rotating matter. Okay, so here is the center of the rotation. And so this is rotating. Okay, and if you have the inhomogeneous pressure, then the pressure gradient gives you the force. And in this way, if you have a larger pressure outside, then the pressure gradient is directed inward, right? And this inward force should be balanced with a centrifugal force. And in such a way, if you have such a centrifugal force due to the rotation, you must have larger pressure outside, okay? So this is actually explained in this way using some, the simple expressions. But anyway, the intuitive picture is this, okay? But the larger pressure means smaller free energy. And as I told you, the Polyakov loop is given by this free energy gain on the exponential. And the smaller free energy means larger Polyakov loop. But the lattice people found that smaller Polyakov loop. So this very simple and natural explanation goes in the completely opposite direction to the lattice observation. So the lattice result is very puzzling. I must say that this is really unbelievable. Okay? But I know that the Victor is a very careful person, so I believe in his results. But anyway, this is very mysterious. Okay, now it's time to summarize my talk. Well, the finite temperature, density phase diagram, there are many scenarios and huge uncertainties, but there in the by the topological argument, there might be some chance to define the Quark matter interface. So this is actually very exciting possibility. But still, there are many, controversial arguments, and there is no conclusive answer yet. And the finite magnetic field business is more or less very well understood. But the finite rotation situation is even more controversial, and the lattice and all the successful models are actually inconsistent, and I have no idea how to resolve this inconsistency, but which means that this is a big theory challenge, and so we are all excited. Thank you very much.
Thank you, Professor Fukushima, for this really nice talk. We have time for a couple of questions. If anyone has a question, only raise your hand or unmute your microphone and ask directly, please.
Luis, with your permission, I have a question.
Sure, Aftab.
Thank you very much, Professor. I have just a question about that, about your omega, no? When you were discussing these things, no? So is there some sort of Roberg symmetry or no? Like if you add imaginary chemical potential?
That is very interesting. That is very interesting. Okay, so in analogy to the imaginary chemical potential, I see. Oh, that is very interesting. I have never thought of that. But it is a bit difficult to see such kind of symmetry. That is because the chemical potential and rotation velocity are quite analogous, but not really the same thing. And the difference can be seen here. So this J, what is this J? This J is actually, you have to take the summation over all possible, the angular momentum. This is a sort of the momentum, right? Instead of the momentum phase space integration, you have to take the angular momentum sum. Okay, and so, well, so this is a superposition, a sort of a superposition of many different chemical potentials. So, okay, honestly, I don't know if there is such kind of a symmetry or not. That is very interesting question. Okay.
Okay, thank you very much.
Right, some other question?
I have one question.
Yes, sure, Fabi.
Thank you. It's a very naive question. I wonder is there a way to test experimentally that region of duality that you told us about?
Well, so the success of the thermal fit is a sort of evidence for the validity of a duality. So as I told you, okay. So the thermal model fit is surprisingly successful. And well, yes, yes, okay, so well, yes, yeah, okay, so now, okay, it is taking some time to show the page, sorry. Yes, this one. Okay, this one. So this is surprisingly a successful fit to explain the experimental data. And so, of course, in experiment, you can access only the information of a hadronic matter. And so you can never get the information of a quark-gluon plasma because the detector can just measure the number of hadrons. But still, this is quite impressive because this temperature and density is quite close to the phase boundary. And so this carries some information of deconfined matter. And that is actually, some hint of the validity of the duality. That if there is no duality, or if there is a first order phase transition, so this kind of description should not work, right? So this is a sort of evidence.
Okay, thank you.
All right. Well, thanks a lot, Professor Fukushima, for this nice talk. And now we continue with the program. Javier, are you there?
Yes, I am here. Can you hear me?
Yes.
Let me put my video on. Okay, let's continue to go next presentation. Christian, I think is here. Can you please share your slides?
Yes, I'm trying to.
Okay, thank you.
Here we are. So now you should be able to see.
Yes, okay.
Talk and hear my voice.
Oh, yes, we can do both. Okay, we are a bit late, so we still have 50 minutes, of course, for your presentation. But let me just be quick and just first thank you for accepting for this to give this presentation. Well, let me just say a few words about you. I will not say many things. Christian is one of the leading experts in perturbative QCD using the Dyson, Schwinger, and Peter and Faddeev equations for Hydron physics, and he will tell us about the work he has been doing recently and along the years in this field. Please, Christian.
Thank you very much for the kind introduction. It's a great pleasure to me to follow up on Kenji's talk. We're actually now choosing a different field, right? So we're not concerned with finite temperature chemical potential, but with hadron physics. So zero chemical potential, zero temperature. And I will cover a couple of results which have been summarized in these two review articles. One basically on baryons, but also on the details of the Dyson-Schwinger Peter approach. And the other one is a short review on our work on 4 quark states, Tetra quarks. So I will briefly start the talk with an introduction into quark mass generation. And you will actually see that that matches nicely to what Kenji explained with respect to chiral symmetry breaking. And I will then cover in 3 chapters the light quark sector. We will start with light mesons, with conventional light mesons, so 2 quark state, and compare those with potential 4 quark states in certain channels. Then there will be a very brief section on our results on glue balls, also in the light energy sector. And then basically the main part of the talk will be on light and strange baryons. And if I have time at the end, I will then go to the heavy quark sector and talk a little bit about Chamonia and heavy light 4 quark states. So let me again go into this very fundamental picture of mass generation. The proton has a mass of 938 MeV. Right, and if you just know that quarks acquire mass from the electroweak force, from the Higgs mechanism, of course you wonder where the mass of the proton comes from, because the up and down quarks that make up the proton are actually only have a very small mass. That depends on the ionization point and the scheme, but they are of the order of 3 to 7 MeV. However, if you look at a strong force, this is completely different. First of all, there is no distinction between the different flavors. So QCD treats all flavors equally. And QCD provides a substantial amount of mass to all these quarks of about 350 MeV. Of course, for the heavy guys, you hardly notice this additional mass, right? So the bottom and the top quark are certainly dominated by their electroweak part. But for the light quarks, of course, this is the major contribution. And considering the proton, actually, it is fair to say that almost 99% of all the mass that we see in nature, which comes in the protons and neutrons, are generated by the strong force. And actually, this was an issue for a Nobel Prize in 2008. Now, the equation that deals with this mass generation on a fundamental level is the Dyson-Schwinger equation for the Quark propagator. And I will try to explain how this equation does that. Let's have a brief look at the structure of this equation. On the right-hand side here, what I denote with this dashed line is a quark that goes through space and time without any interactions. That's a bare quark as expressed in the Lagrange density of QCD. And then we have a self-energy diagram, which explains all the infinitely many ways how a quark can interact with itself, namely by emitting and absorbing gluons. 1 gluon, 2 gluons, 50 gluons, infinitely many gluons. As a result of this interaction, we see on the left-hand side of this equation no longer a bare quark, but a so-called dressed quark, which is denoted with this blob here. And that contains the full physics of quarks propagating through space and time and interacting with itself. Now, the interesting feature about this equation is that this fully dressed quark propagator also appears in the self-energy on the right-hand side. So if you want to solve this equation, you have to solve itself consistently. And you have to know the additional inputs, which is the fully dressed gluon and the fully dressed quark-gluon vertex. I will come back to these elements in a couple of slides. But first, let's have a look at this mass generation business again. How can we explain physically what happens? Imagine you have a party, lots of people going around in a crowded room, and there's one very, very famous person entering this room. Now, with all these people in the room, this person could cross the room quite quickly, just propagate through the room without interacting with anything because there is nothing there. However, since this person is very famous and all the people would like to interact with him, shake his hand, raise glasses with him, he attracts a crowd of people around him. And moving in this crowded room is now very different for our famous person. If he wants to accelerate, he also needs to accelerate the crowd of people clinging to him. if he wants to decelerate, he also needs to decelerate this ground. And in effect, he has acquired a lot of extra mass. And this is actually a good picture, which was originally invented for the Higgs mechanism, but it's also a good picture to explain mass generation here for our quark. What we see is an effective quark, a dressed quark, which is made up of our bare quark and lots of gluons which interact with it. And that substantially changes the nature of this quantity. Now, how do we calculate this effect? First of all, let me emphasize that this equation here, as it stands, is exact. It can be derived exactly from the generating functional of QCD, which we have here in one version. But as you've seen previously, in order to determine this quark here, we also need to know about the gluon, and we need to know about the quark-gluon vertex. So where do we get these quantities? Well, there are additional equations that describe the behavior of these guys. The fully dressed inverse gluon propagator can be expressed as the bare one, the gluon just going through space and time, and lots of different possible interactions. The gluon interacting with itself by a gluon loop, and that the 3-gluon vertex plays a major role here. The gluon interacting with quarks by emitting and absorbing a quark-antiquark pair. The gluon interacting with extra particles which appear due to gauge fixing, the so-called Fadeev-Popov ghosts. And those again are described by another Dyson-Schwinger equation. And then we have these fully dressed vertices, which are again expressed by Dyson-Schwinger equations. This is the one for the 3-gluon vertex. This is the one for the ghost-gluon vertex. This is the one for the quark-gluon vertex. And usually in these equations, we again have 4-point functions. Then there are equations for the 4-point functions, which involve 5-point functions, and so on, and so on, and so on, and so on. So these exact system of equations form an infinite tower, which can only be solved in certain limits, not in general. So if you want to have general solutions of these equations at the general momenta, you have to truncate, you have to break this infinite tower at some point. And this I've already done here. If you have a close look, for example, at the equation for the quark-gluon vertex, you see on the right-hand side, we have the bare one. We have a diagram which involves 2 gluons and again a quark and 3 gluon and quark-gluon vertices, and another one which again just involves these quantities. The original equation already involved a 4-point function, but I have approximated this 4-point function by a so-called skeleton of a quark and 2 fully dressed vertices. And in this way, I managed to close these equations. What you see here is still a tremendously complicated problem, and not many people up to now have actually achieved solutions of these type of equations. But this is the most advanced, this and corresponding truncations in other frameworks is the most advanced calculation which we can do in this framework. And this particular combination has been solved by Richard Williams first in 2016. And there are similar ones which are solved by Markus Huber quite recently. And there is work in the related framework of the functionalization group, which is of similar quality. Now, since this is so complicated, we can only do some calculations in this highly complicated framework. For many, many phenomenological applications, we do something much more simple. We actually stay at the level of the quark equation and combine the dressings of the gluon and the dressings of this vertex into one function, which we call an effective coupling, which then only depends on the gluon momentum. And for reasons I don't have time to explain, this is called a rainbow ladder approximation. And then for this function, you just use a model, which actually contains 2 parameters, which you adjust to physics, usually to the pion decay constant, and one parameter can be varied. And all the results that I will present you in the following are obtained in one of these 2 approximation schemes, either in the full calculation with this full scheme here, or just in this rainbow ladder approximation. And I will actually compare results from these 2 calculations. So this was probably the most technical slide in my whole presentation. So you can relax now. So what do we get typically when we solve these equations? The Quark propagator is not a very complicated structure. It actually has two different Dirac structures, a p slash and the one in Dirac space, and can be parameterized in terms of two functions, the Quark mass function and the Quark wave function. And what I show here is the Quark mass function on a linear scale as a function of space-like momentum, and the Quark wave function, again on a linear scale, and again as a function of space-like momentum. And I compare lattice calculations of these quantities with results from Dyson-Schwinger equations in two frameworks, which are called quenched and unquenched. Quenched just means that, quenched means that these type of contributions, closed quark loops, are neglected. And one can do so on the lattice, and one can also do so in Dyson-Schwinger. And unquenched means that they are included. And what you see is that generally the lattice and the Dyson-Schwinger results, first of all, agree with each other. So they describe the same physics. And what you see here is that the Quark mass function is actually a continuous function that is small at large momenta. What you basically see here is the current quark mass, so the mass which is generated by the electroweak interaction. And at small momenta, you see the additional mass which is generated by the strong interaction of the order of 350 MeV, as Kenji already pointed out. So the quark looks very different at different momenta. And also its wave function looks different. At large momenta, the wave function is close to 1. And the wave function is actually a measure of the compositeness of a particle. If it's close to 1, it means that it's just a particle. And that's just your current quark, your quark without much around. Whereas here, at low momentum, where QCD interaction is strong, ZF is widely different from 1, which just tells you that your quark is now not just a quark, but a quark surrounded by a cloud of gluons due to the interaction with itself. So that's the picture behind dynamical chirosymmetry breaking, which generates this dynamical mass generation. And then we can take these quarks and do calculations for spectra. And we start with light mesons. Let me first motivate why it is interesting not just look at conventional mesons, QQ bar states, but also at mesons which are more complicated, which do not only contain QQ bar, but QQ, Q bar, Q bar. And this is motivated by experiment, since at experiments like Bell, Barbar, BESS, or LHCb, many states have been found which do not fit the conventional QQ bar picture. And a possible explanation for at least some of these states is that they are so-called 4-quark states, Tetra quarks, which is quite accepted. The interesting bit of information which we would like to extract is, what is the internal structure of these Tetra quarks? Are these tightly bound compact objects of a heavy quark antiquark pair and a light quark antiquark pair? Is the internal structure such that these Tetra quarks are decomposed into a heavy light diquark and a heavy light anti-diquark? Or is it decomposed into two colorless components, like a heavy light quark antiquark pair and a corresponding heavy light quark antiquark pair? Or are the two heavy quarks sitting together and the light quarks are going around? This is a very interesting question to answer because it is related to the underlying QCD dynamics. The interaction between these quarks determine which of these structures is realized. And certainly in order to study this, you need a framework which can assess all these possibilities. And I will argue later on that the Dyson-Schwinger Peter framework is the framework that can actually do that. Okay, but let's first have a look at the light meson spectrum. What can we expect? These are some states extracted from the PDG. Actually, I extracted in each of the channels, pseudoscalar, vector, scalar, axial vectors, just some sample states. And to me, the most interesting channel is actually the scalar channel. it is interesting because below 1 GeV, we actually find a light nonet in the PDG, which I did not put into this diagram for reasons I will explain in a second. And we find a heavy nonet where I put one member of this heavy nonet in this diagram. Why didn't I not put the light nonet into this? Because I only wanted to include the conventional QQ bar states in this diagram. And there has been an argument long ago, actually by Jaffe in 1977, that the light QQ bar nonet in the 0++ channel cannot be QQ bar. Why is that? Well, here we see the nonet. And we see that some of these states contain just light quarks, some of these contain 2 strange quarks, and some of these contain 1 strange quark. Our strange quark is much heavier than an up-down quark, so you would expect a mass ordering according to the strange quark content of these states. However, this is not what we see with the conventional QQ bar assignment. For example, the F0980, which is SS bar, has the same mass as the A0980, which is the U bar. Why? No idea. If, in contrast, you assume that these states are not conventional QQ bar, but actually contain 2 quarks and 2 antiquarks, everything falls into place. The lightest state, the F0500, just contains up and down quarks. The intermediate states, the kappas, contain 1 strange quark. And the heavy states, the F0 and A0980s, contain 2 strange quarks. So very, very natural to make this assumption. So the light nonet, which you see in the 0++, is very, very likely not a QQ bar state. I will come back to this in a second. Now, how do we extract these spectra from our Dyson-Schwinger Peter framework? I will demonstrate this for conventional mesons, for QQ bar states, and then everything else is quite similar. In the functional framework, where you see these states is a 4-point function, which I call G, which contains an incoming quark-antiquark pair and an outgoing quark-antiquark pair. And if the total momenta of this pair hits a meson pole, you can actually convert this diagram into a diagram which looks like this, where we here have a propagator of this meson, and here we have a so-called beta-salpeter wave function, which tells you how this meson contains a quark and an antiquark. And if I take this quantity and evaluate it at this pole, I get all the informations on this meson. And actually on the lattice, you do the very same thing. You work with this 4-quark correlator, you connect the external lines to quark-antiquark sinks and sources, and you extract plateaus in your Euclidean correlators, which signal the masses of these mesons. So very, very similar framework. Now, from the defining equation of this quantity, you can actually extract a beta-salpeter equation for these wave functions here. On the right-hand side, you have the wave function. On the right-hand side, you have the wave function again. You have the quark and the antiquark that propagate, and a so-called K-matrix, which contains all the possible interactions between this quark and an antiquark. And this is actually the equation that we're solving. This K-matrix has certain properties which connect it to the quark self-energy. In particular, it has to satisfy a relation which is called the axial vector Wo-Takahashi identity. And if it does so, and only if it does so, then all the chiral properties of the theory, in particular, all the requirements from dynamic chiral symmetry breaking, and in particular, the Goldstone boson nature of the pion, are satisfied. So doing an approximation, a truncation, which satisfies this basic requirements, guarantees that the pion is actually massless in the chiral limit of vanishing current quark mass and gets the correct mass at the physical point. So this is very, very important in all approximations that you're doing in this framework. Okay, so what do you get? Remember, we had these 2 different approximations. The rainbow ladder was the simple one, where we just solved the quark DSE with some effective running coupling and then put the results into the beta-salpeter equation for a meson. And we have the complicated one where we solve a lot of equations together and then put the result into the beta-salpeter of the equation of the meson. The rainbow ladder result is shown here in blue. We see that we get the ground state right in the pseudoscalar channel, and we get the ground state right in the vector channel. So that's fine. This is clearly a success of the rainbow ladder calculation. In the scalar channel, looks horrible. Axial vector channels, mass is much too low. In other channels, which are called exotic channels, for reasons I will explain later, rainbow ladder sees states which are not present in the experiment. So clearly, rainbow ladder is useful when you know what you're doing and apply it to channels where you know that it works, and it's not useful in other channels. So this is a caveat which one has to take into account. If, however, one uses this fully advanced truncation, everything falls into place. You get the ground state and the first radial excitation in the pseudoscalar channel, ground state, first radial excitation in the vector channel. The 0++ state is now above 1 GeV, where it should be, according to Jaffe's argument, right? It should be part of it should correspond to the heavy known there. The axial vectors fall into place. And even in the exotic channels, we find states which are close to states which are extracted from experiment. So it really pays off to do this horribly complicated calculation. Unfortunately, the mesons are the only place where we can do these calculations. And we have to work harder to do the same type of quality results for baryons and for tetra quarks. So all the results which I show you from now on have been obtained, with the exception of the glue ball, have been obtained in the simpler rainbow ladder calculation. Speaking of the glue ball, we actually also find the glue ball here in the 0++ channel at around 1700 MeV. And that's very interesting. So this is certainly something which we should look at in more detail. I will come back to this. But before we come to the glue ball, let's have a look at the missing states here, at the states which we believe are not QQ bar states, but actually 4-quark states. In order to describe these 4-quark states, we can also solve a Peters-Peter equation. Here it is. It is much more complicated than the one for the mesons. On the left-hand side, you have a Peters-Peter wave function, which describes how this 4-quark states contains 2 quarks and 2 antiquarks. And on the right-hand side, we have some diagrams which describe two-body interactions between these quarks. So that kernel is actually it's actually the same as the one that you saw in the Meson BSE. And then there are 2 additional terms, one that describes irreducible 3-body interactions, so 3 of the 4 quarks interact with each other, and one which describes irreducible 4-body interactions. Now, unfortunately, we can't do those. They are just too complicated. I will argue, however, later on that we don't need to do these. Remember the discussion I had previously on the internal structure of our 4-quark states. If it so happens that internally clusters of 2 particles form, either diquark, anti-diquark, or meson clusters, or hydrogen-ammonium clusters, then the only reason these clusters form is that these forces are dominant. If these forces are dominant, you would expect some compact tetraquark structure. So by neglecting these, I say, okay, I will not allow for this possibility, but I will still allow for these possibilities. And I will actually argue that these are this is the right way to look at this equation. If you bear with me for a couple more slides. Furthermore, all these internal clusters have quantum numbers which are fine in rainbow ladder. So it's actually justified that these quantities here are approximated in this rainbow ladder scheme that I explained a couple of minutes ago. One word on the Peters-Peter wave functions, which I need to explain one of the most prominent features of these equations. So these are quite complicated. These are horrible beasts, actually. They contain dressing functions which depend on 9 Lorentz scalars. They are built from 1 total momentum and 3 relative momenta inside these 4-quark states. 256 Dirac tensors, horrible, and lots of colors and flavor structures. And we have to reduce this complexity into structures which are guided by physics. So we actually single out 20 of these tensor structures. We also need to reduce complexity here. And in order to do this, the permutation group comes into play. And this is, again, probably one of the most complicated transparencies that I have. So please stay with me for a second, and then we'll see, we'll have a look at the results. It turns out that all these relative momenta can be grouped in multiplets of this permutation group. There is a singlet, which is basically a scale, and there is a doublet of two particular combinations of these relative momenta. So these doublets go into each other when the role of quarks and antiquarks, for example, are interchanged. And these are very interesting because if you look at the plane of these two momenta, then this triangle here is the region which is integrated over in my Bethe-Salpeter equation. So this is the momentum region which is probed by the Bethe-Salpeter equation. And it turns out that if, for example, inside my 4-quark state, here I have the example of a heavy light one, but this also may occur in a light one. If, for example, the C bar and the Q bar develop strong correlations into a colorless meson, and at the same time, the C and Q bar also develop these correlations, then these will appear as poles in this momentum plane. The same thing for heterogemonia structure. Those will appear as poles here on this line. And if the diquarks are the dominating degrees of freedom inside my 4-quark states, they will develop poles here. Now, since these are poles, the closer these are to the integration region, the more they will dominate the equation. It is thus a very, very interesting dynamical question to ask which of these poles, which of these pole types are closest to the integration region and therefore dominate the equation. And by this process, we can actually decide which ones of these internal structures is most likely to be realized in nature, has the most influence on our 4-quark state. So this allows us to assess the internal structure of these 4-quark states. Let me demonstrate this as the example of this light scalar 4-quark states. So first of all, I do not take into account the dependence on this doublet. I only take into account the leading dependence on the singlet. And this is tantamount or equivalent to not allowing internal clustering at all. So what we're now calculating is just a bound state of 2 quarks and 2 antiquarks with a mass of roughly 350 MeV. And what you find from your Bethe-Salpeter equation is a bound state of roughly 1200 MeV, which is probably what you would expect. 4 times 350 minus some binding energy should give a state of 1200. But then, in addition, I allow this dependence. I allow for internal clustering, and something absolutely miraculous happens. The mass goes down to 400 MeV, roughly, give or take 50 MeV. And the dominating clusters inside the scalar states have the quantum numbers of pions. So this shows you that the two-body interaction inside this 4-quark state is strong enough to form 2 pion clusters. And the resulting state is actually a 2-pion resonance. And we see that from our equation. And this is precisely what you expect. The F0500, the lowest state in this 4-quark nonet that I showed you, has a mass of roughly 450 MeV, and it is known to be dominated by 2 pion clusters because it decays heavily into 2 pions. It has a very, very large decay width. So that's very, very interesting. We can identify this state with the F0500. We can also do this game with strange quarks. We find for the kappas masses of roughly 750, 800 MeV, and for the A0, F0 masses of roughly 1080 MeV. So the correct mass ordering as suggested by Yaffe. And in all these calculations, the Meson components dominate over the diquarks. So a diquark anti-diquark approximation is definitely a very, very bad approximation for these type of states. The Meson clusters just dominate. We can also investigate the mixing of these states with conventional QQ bar states, and we have found that the net effect is actually very small. Shifts of a dozen MeV probably, but not affecting the result in a global level. Okay, so that is very satisfying, and it's actually a model-independent result. These meson clusters will always be more important than the diquark, simply because the QCD interaction in these meson channels is a factor of 2 larger, this is a color factor, than in the diquark channels. So no matter, this will not change if you change the model. Okay, so this is all about what I have to say about light 4-quark states. Now let's have a very, very brief look at the glue balls. What we know from the lattice with respect to glue balls is that the spectrum in quenched QCD, actually in Yang-Mills theory, so the theory without quarks, looks like this. The 0++ is the lightest one, and then depending on the quantum numbers, the others are heavier. And the 0++ is around 1800 MeV. And the reliable results on the lattice have only been obtained in this theory without dynamic quarks. All the full calculations are on a very, very exploratory level. Now, with our Dyson Schwinger beta framework, we can also calculate glue balls. For us, glue balls are states which contain either 2 gluons or, for certain quantum numbers, a ghost-anti-ghost pair. And they form a coupled system of equations where these 2 gluons interact, for example, via gluon exchange, or the ghost state also via gluon exchange, or here via ghost exchange. There have been a number of groups working on this issue with simple models. And what is new now is that we managed to do this calculation with a very, very high quality input from such a 3-pi truncation. So truncation, which includes Dyson Schwinger equations for the gluon, the ghost, the 3-gluon vertex, the ghost gluon vertex, the 4-gluon vertex, coupled together self-consistently, and then use this input into these equations. And the results are like this. So here we compare in different channels the results from the beta framework with the lattice results of Morningstar and Pearden from '99 and a very recent result from Atenodou and Tepper in 2020. And I show results for this in the scalar channel 0++, the first radial excitation, the second radial excitation, and the pseudoscalar channel, ground state, first radial excitation, second radial excitation. And actually one sees that the 2 approaches nicely agree with each other. So there's very good agreement between the lattice and Dyson Schwinger beta framework. It's also interesting to look at the internal structure. What one actually sees is that the excited state is dominated by different basis elements than the ground state. I don't have the time to explain this in more detail here. I will come back to this issue when we discuss baryons. And clearly now the next step is to do different quantum numbers and to go beyond this pure Yang-Mills calculation and include quarks. And we're working on this currently. Okay, in the next 20 minutes maybe, let me focus on light and strange baryons. And then we'll have 5 minutes left for the heavy light states. Let me first discuss about some physics issues that are interesting when we look at baryons. This is a quite old plot from 2001 from the Bonn group. And it shows, first of all, the experimental results, experimental extractions of baryon masses of the baryon spectrum that were known in 2001. So here, for example, we see the proton, the neutron, the first radial excitation, the second radial excitation, and so on, in the 1/2 plus, 3/2 plus, 5/2 plus, 7/2 plus channels, 9/2 plus even, and in the corresponding negative parity channels, 1/2 minus, 3/2 minus, 5/2 minus, and so on. And these are compared with the results of a quark model calculation with 2 different parameter sets, B and A. Let's forget about B, let's just focus on A. And what you see from this plot are 2 things. First of all, the quark model predicts many, many more states that have been observed in experiment. And this is known as the missing resonance problem. Of course, potential solutions to these problems can be twofold. One reason could be that, well, we just did not have identified all the states yet in experiment. And certainly this is true, and this is an ongoing business, and in the past 20 years, many more states have been added, but still, there are many, many more quark model states than have been identified in experiment. So that's the other point. It could mean that the quark model is simply too abundant, too generous, and just produces artificially too many states. And that's, of course, an interesting question to investigate. The second interesting question is, have a look at the ground state and the first radial excitation here in the nucleon channel compared to the negative parity channel. And you find that the ground state in the 1/2 minus channel has a larger mass than the first radial excitation in the 1/2 plus channel. And this is very, very unnatural. A typical quark model result goes the other way around. And this is precisely what you find in the quark model. The ground state in the 1/2 minus is lower than the first radial excitation in the 1/2 plus. There may be many reasons why the so-called famous Roper resonance is so low in mass, and I will actually discuss two possible reasons for that. Now, how do we do this calculation in the Dyson-Schwinger beta framework? And there are actually many different approaches for this. If you start with the Quark DSE, we discussed this, there are two ways to proceed. One way is to proceed directly to the three-body Fadeev equation, where here you have the wave function of a baryon consisting of 3 quarks, and on the right-hand side, you have all the possible two-body interactions between these quarks. And if you know your quark as input and you know the interaction, again, rainbow ladder, you can go on and calculate baryon spectra from this equation. However, since this is quite complicated, people have searched for shortcuts, and one of the shortcuts is you take the quark and calculate a diquark beta equation from that, and you plug that into an equation which describes the baryon in terms of a quark-diquark degrees of freedom. So that's the baryon wave function in terms of diquarks and quarks, and the diquark and the quark interact with each other by quark exchange. So the diquark here splits into 2 quarks and then recombines here again into a diquark quark. That's the second possibility. And I will actually compare results from this and from this framework. And then there is yet another shortcut where you do not solve the Dyson-Schwinger equation at all, but you use Ansätze for your quark propagators and your diquark beta amplitudes and your diquark propagators, and then solve this equation. And I will call this a quark-diquark model. All of these, so here we have the quark-diquark model. Here we have the Dyson-Schwinger based framework in rainbow ladder, in quark-diquark, or three-body quantities. And here there's an even simpler approach where you do some NGL type calculations in the quark-diquark model. All of these approaches are justified. We need the results from all of these approaches, and we need a comparison of results from all of these approaches to get the whole picture. For example, it's very interesting to compare an NGL calculation with a full-fledged rainbow ladder calculation, because here you take into account momentum dependencies in the quarks, in the diquarks, and so on, which are not present here. And the differences in the result actually tells you something about the momentum running of observable quantities, which depend on the momentum running of underlying quantities like the quarks, like the quark mass, for example. Okay, here we see the observables in the up-down sector, nucleon delta masses, electromagnetic form factors, transitions, excited states, transitions in the parity plus, parity minus sectors. Here we have the strange quark sector, ground states, excited states, form factors, and we have the heavy quark sector, ground states, excited states. So a lot of this has been done. What is obvious is that there's a missing column, and the missing column is the beyond rainbow ladder column, the column where we invoke this highly complex calculations. And so there's still a lot of work to be done. I cannot talk about all these results, so I will pick some of the results which are dear to my heart. So let's first discuss the light baryon spectrum. Here again, we have some of the quantum numbers which we saw previously in the quark model calculations. 1/2 plus, 1/2 minus, and 3/2 plus, 3/2 minus. And what I compare is results from the quark-diquark framework in this rainbow ladder approach. So we are now in this channel here, the full-fledged Dyson Schwinger rainbow ladder with quark-diquark. And later on, I will also include results from this channel, the Dyson Schwinger with the three-body equation. Okay, this is quark-diquark compared with the PDG results, and these are updated. So this is now state-of-the-art PDG. And what you see is that below 2 GeV, for every state which you find in the Dyson Schwinger Faddeev framework, there is one state in the PDG. So there is certainly no missing state problem below 2 GeV. And of course, it would be very interesting if we would be able to extend these calculations above 2 GeV. Again, we're working on that. The same is true in the delta channel, 1/2 plus, 1/2 minus, 3/2 plus, 3/2 minus. Again, one state theory, one state experiment, very, very nice agreement. And this whole calculation just have 3 parameters, 2 in the directions, one extra one, and the quark masses. So I think this is quite a very satisfying result. So to my understanding, this is the only theoretical calculation of all these states available. And it's interesting that the level ordering between the quark-diquark in the 1/2 plus and 1 minus is actually the same as experiment. So our first radial excitation here in the 1/2 plus is lower than the ground state in the 1/2 minus. So the functional framework does something right, which the quark model does wrong. However, there's still a difference to the experimental state, at least in this calculation. So of course, the roper may be more than just a 3 quark state. There may be lots of additional mesonic corrections, and actually this is what many of my colleagues believe. But the global level ordering is fine. So, and this can also be compared with the result in the 3-body framework. Since this is much more complicated, we only managed to do the ground state and first radial excitation here in the 1/2 plus, and ground state and first radial excitation in the 3/2 minus. And again, grosso modo, the results agree nicely. Now, what is different in the quark model and in our framework? And that's quite interesting. So the quark model is, in essence, non-relativistics. So in order to make up a baryon with quantum numbers 1/2 plus, you need to combine 3 quarks with spin 1/2. And you can do so such that you get a total spin 1/2 or a total spin 3/2, and 1/2 is the one which is relevant here if L is equal 0, and 3/2 is the one which is relevant here if L is equal 2, because you can combine those to total J 1/2. So these are the 2 contributions which you get in the quark model. And these are the only 2 contributions, and they are the only 2 because this S wave and this D wave contribution need to be even, because parity is connected to L in a 1-to-1 relation, right? In order to get positive parity, L has to be either 0 or 2. In the relativistic framework, this is no longer true. L is not a conserved quantum number. Only J is conserved. Only the total angular momentum is conserved. But this means in a relativistic framework, you can have S-wave contributions, D-wave contribution, but in addition, P-wave contributions. And it turns out that from the 96 contributions from the 64 contributions you get for a nucleon, 8 are S-wave, 20 are D-wave, but 36 are P-wave. And if in some measure you measure the contributions of these S, P, and D waves to the mass of the nucleon, you see that the nucleon is actually dominated from the S-wave contributions, whereas the roper is dominated by the P-wave contributions in our calculation. It's dominated by the contributions which are absent in the quark model. So that's one explanation why in a relativistic framework, this level ordering comes out right, whereas in a non-relativistic quark model, you don't get this. Okay, so that was the light sector. Let's have a brief look at the strange baryon spectrum. Here we have the lambda light. Yep.
You have 5 minutes or more.
Yeah, fine. I will finish. I will easily able to finish the baryon and then we'll see.
Thank you.
Yeah. So we have the lambda, but we started late. You have taken that into account, right? So the lambda with one strange quark. We have the sigma with also one strange quark, and we have the cascades with 2 and the omega with 3 strange quarks. And again, we compare the results in the quark-diquark and the 3-quark framework with the corresponding experimental states. You see agreement in some of the channels, but in other channels, actually, we find more states than have been seen in experiment. But alas, this now seems to be a problem with experiment. Experiments with strange quarks are much more difficult to do than in the light quark sector. And indeed, if you go to the new results of the Bonn-Gatchina group as presented at the N-STAR conference in 2019, you find the following. Here, where we see 2 states and the PDG only sees 1, the new analysis of Bonn-Gatchina finds 2 states. Here, where we saw 3 states, PDG only has 1, the new analysis of Bonn-Gatchina sees 3 states. Here, where we see 3 states, PDG has 2, new analysis, Bonn-Gatchina, 3 states. So it looks as if also here in the strange quark sector, there's a very good one-to-one agreement between what we find in our calculations and experiment. And of course, now here, where there are no data at all right now, our results are predictions for future experiments like Panda, like BlueX and others. Good. If you allow me for 3 more minutes, I'm done with the heavy light states.
Yes, of course.
Very good. So now we leave the baryon sector, and I'm coming back now to the issue of 4 quark states. Remember, this was the equation that we solved, and we can solve this for 4 light quarks, but also for 2 light and 2 heavy quarks. And then again, the issue of the structure will be interesting and important. Here I show you the result in one particular channel, which is very interesting. It's the 1++ channel. This was the channel where the famous X3872 has been discovered by Bell 15 years ago at a mass of shortly below 4 GeV. What I show you here is a calculation in our framework of this 2-charm, 2-light quark state, where we have the masses of the 2-charm quark fixed, and we vary the masses of the 2 light quarks. So what you see here, this is the mass of the 2 light. So if the mass of the 2 light is in the charm region, you actually describe a C bar state, modulo flavor and color structure. And if we go down, at some point, we have a CC bar SS bar state around here. And here at the physical point of the light quarks, we have a CUU bar C bar state. So this is the state which we should compare with the X3872. And we did the calculation including several components. This is the heavy light Meson components. So internal clustering into a D and a D star Meson. This is a calculation when we include in addition the hydrogermanium component, forming the quantum numbers of a J psi, a CC bar in the center, and the light omega going around that. And this is the calculation where we include the possibility of the heavy light Meson clustering, the hydrogermanium clustering, and the diquark clustering, containing an axial vector diquark and a scalar diquark with the right quantum numbers. And what you see is that the results for all 3 calculations agree. And this in turn means that this state is dominated by the DD bar component. So this state, this X3872, as it comes out in our calculation, is dominated by this DD star. And this is completely in accordance with a picture which is called a Meson molecule picture. That you have this DD star, and if the binding energy is small, these form components which are actually quite apart from each other. And this is in agreement with calculations in effective field theory approaches. So that's very nice. There are a couple of crude approximations which drive up our error bar here, so we cannot make very precise statements here, but the overall picture seems to be right. And you find the same in other channels, which I don't take the time to explain. So let me come to my summary. We've made a tour through several areas of hadron physics, dealt with functional methods. And what I really like with this functional method framework, is that it's one framework for all areas of hadron physics. You can use this framework to do mesons, to do baryons, to do exotic states, 4-quark states, glue balls, hybrids. You can do the same framework for form vectors, even to hadronic contributions to G-2 standard model. You will hear a talk later in this workshop on that. And it gives us access to dynamic characteristic breaking on confinement. And I think this makes it a very, very interesting tool. So you're not doing a model for this, a model for this, and a different model for this, but it's really, it's one framework. The main challenge is the systematic control over the error budget. So a priori, when you just do your rainbow ladder approximation, you don't know what you throw away. You need to compare with lattice, with experiment in order to find out. And also with this more advanced truncation. You hope, and we actually see by comparing with experimental spectra, that our structure is now rich enough to cover probably most of the physics. But this needs to be verified, and it is very hard to verify this on a quantitative level. You will hardly be in a position where you say, this is a calculation where I definitely know that my error is only 5%. But for many, many things, this is perfectly fine. It's not always high precision physics, but the framework makes competitive contributions in many areas of hadron physics in terms of structure, in terms of understanding what we're seeing. And I think this is the main strength of this framework. So with that, thank you very much for your attention.
Thank you very much for this very nice presentation about the hadron mass spectrum. Okay, we're a bit late, but I think we have, well, we can have a question, an urgent question from students. This is a school, so this is for you students. I think you should ask something you want, of course. Just speak up. Yeah, a bit shy, maybe. Okay. Let me. Let's thank Christian again. Thank you very much, Christian, for this very nice presentation. We hope to see you at some point in person. Thank you very much.
Thank you.
Okay, is there a question, Fabi? Or your hand is? It's a clap.
No, yeah,
you're clapping. You're clapping. Okay, thank you. Sorry. Okay, thank you, Christian. Okay, I think, well, we are a bit late. I don't know, maybe is here. What should we do? Should we go for a break, or we just move to the next presentation?
I think we move to Avelino's course.
Okay. Okay, Carlos is the chairman now.
Yes, thank you. Thank you, Javier. Okay, so we have the second part of Avelino's lectures on neutrino masses. Please, Avelino, can you share your screen?
Yeah, let me try. It seems I have a problem sharing the screen. Give me a second.
Yes.
Okay. Actually, I think I'll need a minute because I will need to reboot.
Of course.
Sorry.
Don't worry. No worries. Okay, let's wait for Avelino. In the meantime, I probably can give you the instructions for the proceedings. So let me just find them, and share them with you. Okay, let me share my screen now. Please, someone indicate me if my screen is visible. Okay. So these are the instructions for the proceedings. The proceedings are going to be published in the Suplemento de la Revista Mexicana de Física. All contributions will be peer-reviewed according to the standards of the journal, and you can download a template for the proceedings in the author guidelines of the Revista Mexicana de Física. The instructions for the number of pages are the following. We have 4 plenary speakers, 8 pages, for parallel session speakers 6, and 8 pages per hour in the case of lectures. My screen just froze.
So I should be back. Am I back?
Is it visible for you, the information?
Yes.
Okay. So I will stop sharing and start again because I have a problem too. Okay. So please submit your article into the corresponding platform, and send a copy to Xiomara. I think I need to sign out too. Sorry.
Don't worry, we take care. Now we can just move to Avelino if you can stop sharing.
Okay, thank you.
Yes, I'm back. Okay, so let's see if today I don't have the technical problems I had yesterday. So you can see the slides.
Yes.
And you can
your
see
cursor and your cursor as well. Everything.
Ah, perfect, perfect. So you see everything today. Perfect. Okay, so let's go with the second part of the lectures. So today I'm going to discuss Majorana mass models. So I will focus on a particular type of models, which are maybe the most popular ones. So I remind you from what we had yesterday that there are 2 things that we need for every neutrino mass model to work. First, of course, we need to give masses to the neutrinos. That's the main point. And second, it would be great, and actually this is very important and mandatory, to explain why neutrinos are so large. But there are, of course, some extra things that we may be interested about. For instance, we may want our model to be simple, economical, so with very few ingredients. Also, it would be great if it makes sense in a wider sense, in a wider framework. For example, if it makes sense in the context of grand unification or other ideas. And finally, and this is also very interesting, if you can also solve other problems in physics, like for instance dark matter or the flavor problem, then even better. Okay, so there are many extras, but the 2 mandatory ingredients is to give mass to neutrinos and to explain why they are so light. I remind you also from yesterday that when you do effective field theory and you add additional higher dimensional operators to the standard model Lagrangian, the philosophy that you have in mind is that at some high energy that you call lambda, there's going to be some ultraviolet theory with some additional degrees of freedom, some particles. And when you integrate out these particles and you go to lower energies, you get the standard model plus additional operators. So what we are actually looking for is the ultraviolet completion. We are interested in the theory that is behind neutrino masses. But what we measure at low energies is these extra operators. Therefore, there are in principle many possibilities for the ultraviolet theory. So, and also we discussed yesterday that at dimension 5, there is a single operator, the so-called Weinberg operator, that is compatible with the standard model gauge symmetry. And this is a very important operator for many reasons, in particular for us, because it breaks lepton number in 2 units, and also because when the Higgs gets a BEV, when it breaks the electronic symmetry, it induces Majorana neutrino masses. So here you have a representation of this operator, and the ultraviolet physics is hidden here in the blob. So there are many realizations, many ways to get this blob from ultraviolet completions. And this is what we're going to do today, to see ways in which you can realize this operator with specific models. So this is the summary of the lecture. I will begin with something that I call the master formula. So a formula that basically gives you an idea of what type of models we can have, Majorana mass models. Then I will discuss the seesaw mechanism, which is the most popular model for neutrino masses. And then I will start discussing several variations or several different ideas, like low-scale seesaws, relative models, and models with dimension larger than 5 operators. Then, if I have time, I will discuss some loose ends, some additional comments, and I will conclude with a summary. So the master formula is just this. So this appeared in this paper that I find very pedagogical. So, I mean, Bonnet et al. Doesn't mean a lot, but maybe you don't find the reference, please ask me and I can give it to you. And the idea is that in any Majorana mass model, any Majorana neutrino mass model, the expression for neutrino masses takes this form. There is always a factor that is given here. So the BEV of the Higgs squared divided by some scale, lambda, that you can easily recognize is coming directly from the Weinberg operator. And then there are some additional factors that could be there or could not be there. They depend on the model. So as I said, you always have this minimal factor. This is always there. And this is actually what you have in the seesaw mechanism. You only have this. Now, in some models, you have an extra suppression. You have an additional parameter that I call here generically epsilon, that is typically very, very, very small. So this is what happens, for example, in models that realize the seesaw mechanism at low energies. And this is also what goes under the name of low-scale seesaw. If epsilon is much smaller than 1, you get automatically a reason for the suppression of neutrino masses, even if lambda is not that large. Now, there is another way to suppress neutrino masses, which is to induce it by loops. Each loop will introduce a factor of 16 pi squared, which, as you know, is around 100. So the more loops you have, the more suppression you get. So this is another way to suppress neutrino masses, and this has been used a lot in the literature. And finally, there is a third suppression trick, which is to induce neutrino masses with a dimension larger than 5 operators. So the Weinberg operator is dimension 5, but if you induce neutrino masses by a dimension 7, 9, 11 operator, then you get additional factors of BEV of 5 divided by lambda. If this ratio is smaller than 1, then the larger the dimensionality of the operator, the larger the suppression factor, which is, again, what you really want, to have a suppression factor that explains why neutrinos are lighter than the other particles in the standard model. So let me start with the seesaw mechanism. The seesaw mechanism just uses the first factor, this BEV squared divided by lambda. So you remember that yesterday we did this already. We considered the addition of right-handed neutrinos to the standard model particle content. When you add right-handed neutrinos, you know that they have to be singlets under all symmetries, so singlets under SU3, under SU2, under U1 hypercharge. And you can add several of them. Typically, you need at least 2, because you need to generate 2 different masses for neutrinos to explain the atmospheric scale and the solar scale. But typically, people add 3 just for, to have a replica of what you have for the other fermions in the standard model. But you can do it with 2. This is not very relevant at the moment. In any case, since the right-handed neutrino is a singlet under all symmetries, you can write down a Majorana mass term for it. So you can write down something like this. So nu RC bar MR nu R. This term violates lepton number in 2 units, but it doesn't break any other symmetry. So in principle, it's allowed. Now, when you do that, you get 2 different mass terms. First, from the standard Yukawa, the standard Yukawa with the lepton doublet and the right-handed neutrino, you get a Dirac mass term between the left-handed neutrinos and the right-handed neutrinos, where this MD, this Dirac term, is nothing but the Yukawa times the Higgs Bev. Okay, this is what you have for all the fermions. And now, in addition, you have this Majorana mass term for the right-handed neutrinos. You can write down this in a compact way by using this notation. So here I have defined this chi, which is nothing but a collection of all the possible neutrinos you have, all the possible right-handed neutrinos, to be more precise. Okay, so you can convince yourself easily that this expression is correct, where this matrix here is given by this expression. So you have MD, MD transpose, and MR. It's a symmetric matrix. Now, if MD is much smaller than MR, so if the Dirac mass term is much smaller than the Majorana mass term, then you can diagonalize this in blocks with two different blocks, one here and one here. This one corresponds to the light fermions, to the light neutrinos, and this one to the heavy neutrinos. And in very good approximation, you find that this block over here is nothing but MD transpose MR inverse MD, which goes, as you can see, as Bev of the Higgs squared divided by lambda, where lambda is the mass, this MR, which is the mass of the right-handed neutrinos, of the heavy fields. So this is a realization of what I just said. This is a realization of this factor here. Okay, the typical factor that you have always in Majorana neutrino mass models. This formula is very famous. This is the famous CISO formula, MD transpose MR inverse MD. And the nice thing is that if you want to have Yukawas of order 1, you can do that by having a very large MR scale, like, for example, 10 to the 14 giga-electron volts. As I said, this is a very famous formula, but this is a school and we are supposed to learn things, and I'm sure that most of you already knew this formula. But how do you get this formula? Because we have seen this formula many times. I'm pretty sure that most of you saw it already. But do you know how to derive it? It's not that complicated, but if you have never seen how to derive it, maybe you don't know how to do it. So let me tell you how you can derive this formula. So we started with this mass matrix, and we want to diagonalize it to get something like this. We do it by means of a unitary transformation that I call W. Actually, this is not a diagonalization. If you want to be precise, this is what in mathematics is called a Takagi transformation, because here you have W transpose W. You don't have W inverse. Okay, this is not orthogonal, but a unitary matrix. But there is a theorem that tells you that you can always do that if the matrix here is symmetric. Okay, I cannot prove that theorem in these lectures, but you believe me. You can always do that if the matrix is symmetric, and it is symmetric in this case. Now, you don't know W, and therefore I didn't say much by writing this equation. But there is a nice trick. You can use an ansatz, and this was done by Grimos and Labura in a paper in 2000, a very nice paper that I really recommend you to read. You can write this matrix in this particular way. You introduce another matrix, B, and write W in this way. So you have B, B dagger, and this is square root of the identity minus B, B dagger. So the square root has to be understood as a series expansion, okay? So square root means 1 minus 1 over 2 B, B dagger, and so on, okay? 1 over 8 B, B dagger, B, B dagger, and so on, okay? And maybe some of you already recognize that this ansatz is motivated by the fact that a rotation matrix in 2 dimensions would be something like cosine beta minus sine beta cosine beta. So you see that this B is the equivalent in a matrix form of an angle. Okay, it measures the mixing between the light and the heavy fermions. Now, this is just an ansatz. I just wrote down this matrix in this form just to see if this helps me or not. I can put it back in this expression, and I can express, I can do the multiplication, the matrix multiplication, and concentrate on this 0 here. This 0, when you do this multiplication, corresponds to this expression here. Okay, it's just a very simple exercise. So this quantity here is 0 if this equation is correct. Now, the goal is to find an expression for B in terms of the elements of this matrix, MD and MR. I'm convinced that you cannot see a solution just by looking at this equation. It's pretty complicated. It's a matrix equation, so it's not simple to find a solution, but there is a simple trick. As usual, we are physicists, we work with expansions, and we always do Taylor expansions. So we will consider that B can be written in powers of 1 over MR. So we will have in mind that MR is a very large scale, as we already do in the seesaw mechanism. And we will consider that B can be written as B1 plus B2 plus B3 plus B4 and so on, where each Bi or Bj is proportional to MR to the minus J. So each term in the expansion is supposed to be much smaller than the one before. Okay? When you do that, you can solve this equation at any order you want. For example, you can do it at the first order, at second order, at third order, and that's more or less easy. You can do it order by order. If you do it at leading order, you can easily do it later if you want. The leading order solution to this equation is this one. So B dagger is MR inverse MD transpose. Okay, this is the solution to this equation. And when you have the solution, you can put it back again here in the original expression and find what is the result for M light. And you get this expression, which is the seesaw formula. Okay, so this is the way you can prove the seesaw formula from the original expression of the mass matrix. So now if anyone asks you how to get this formula, you know how to answer. And actually you also know if you wanted to find corrections to this formula, because now I can solve not to leading order, but to next to leading order, to second order in 1 over MR, and you will get this expression plus the correction at the next order, which is very small, but you can calculate if you want. Alternatively, there is another way to find this formula, which is to work using the effective field theory approach. So you can integrate out the heavy right-handed neutrinos at grid level. You don't need to do anything more complicated than that. And also you will get in this way the Weinberg operator, and the coefficient in front of the Weinberg operator would be basically what gives you the seesaw formula. This is an alternative way, also very elegant, to be honest. I like also that way. So it's a matter of taste. Okay. So this is the seesaw mechanism. If you have a very large scale, automatically the light neutrinos are very, very, very light. And this is what people like about the seesaw, that you have a natural explanation for the lightness of neutrinos. But what we saw actually is what people call more precisely type 1 seesaw. Okay, the type 1 seesaw is what we just saw. We introduce right-handed neutrinos, they are singlets, and then you get a diagram like this. So you exchange right-handed neutrinos with the Yukawas here, and you get a formula for neutrino masses which is proportional to the Yukawa square, the depth square divided by MR. But there are two other versions of the seesaw which can also take place at tree level. Very similar to the type 1 seesaw is the type 3 seesaw, which instead of singlets, so right-handed neutrinos, uses fermion triplets. So essentially, instead of a Yukawa with a singlet, uses a Yukawa with a triplet that is also allowed by the gate symmetry. And the sigma 0, so the neutral component in the triplet, plays the same role as the right-handed neutrino in the type 1 seesaw. And the rest is essentially the same. So you get a formula that is very similar to the formula in the type 1 seesaw. There is also a different version that instead of fermions uses a scalar. So you can introduce also a scalar that is a triplet under SU2 and has hypercharge equal 1. So you get a doubly charged scalar, a singly charged scalar, and a neutral scalar. And because of that, because of this particle, you can get this diagram at two levels, where you can also recognize easily that this is nothing but the Weinberg operator. So you have two Higgses and two leptons, thanks to the presence of this scalar. So these are the three ways you can get neutrino masses with the seesaw mechanism at tree level. The type 1 seesaw is the most popular one, but you already know that there are two other versions. So actually, people, when they say seesaw, they typically refer to the type 1 seesaw, but it's actually a paradigm. So the paradigm is that neutrino masses are generated by a very high scale. And how high? We saw already that in order to get Yukawas of order 1, you typically need a seesaw scale, mass for the right-handed neutrinos, at the level of 10 to the 14 GeV, more or less. And this is very close to the grand unification scale, which is typically at the 10 to the 16 giga-electron volt. And this is very nice because it is a very suggestive situation. So in many theories of grand unification, for example, in SO10 theories, you have right-handed neutrinos in your model. For example, in SO10, the 16 plate, so the 16, which is the representation in which all the standard model fermions fit, has also a hole here, which can be filled by the right-handed neutrinos. So you naturally have right-handed neutrinos in this model, and with a coupling with a 126 representation, you get the type 1 seesaw automatically in this model. So this is something that people like a lot, that you can embed the seesaw mechanism very easily in grand unification. However, the bad part or the bad side of the seesaw is that it is impossible to test directly, because there is no way you can reach the energies that are necessary to produce these particles, for example, at the LHC. 10 to the 14, 10 to the 15 GeV, this is way too much for the LHC and for any other experiment. So the situation is somehow like this. So we like the seesaw, we love it because it's a very nice explanation for neutrino masses, but we are not fully happy because we cannot test it directly. That's why people have invented many other modes, many other variations, many other seesaws, many other types of mechanisms to produce neutrino masses. For instance, the low-scale seesaw. This is what I want to tell you now. In this case, we have the first factor, and we have a second factor, which is this epsilon, that is much smaller than 1. So in general, in these models, what you want is to have the factor that you always have, the value of the Higgs squared divided by lambda, but also some parameter in the model, which is very small. What is the idea? That if the parameter is much smaller than 1, then lambda needs not to be that large. You can use lambda much closer to the electroweak scale, because you don't need to suppress neutrino masses with lambda, because you can suppress with epsilon. So you get this additional handle. You can change the typical mass of your seesaw mediators and lower it to a scale that you can reach in experiments. So this is very nice, and this is the main motivation. Also, it is very important that this additional parameter that you introduce, this what I call here generically epsilon, is technically natural. Okay, let me explain for a minute what this means. So with in the limit epsilon going to 0, the model will produce vanishing neutrino masses. You can see directly from the formula. If epsilon is 0, neutrino masses are 0. This is because the limit epsilon going to 0 restores lepton number exactly. So lepton number would be conserved if epsilon is 0. This implies that any correction to epsilon has to be proportional to itself due to symmetry reasons. You cannot give a correction to epsilon with parameters that do not violate lepton number, because they cannot correct a parameter that violates lepton number. So if this parameter is small to start with, it is always small. So it is technically natural and protected from corrections. So that's why, and this is something that was argued by Toft long ago in the 80s, that's why these models are okay. So you can introduce a small parameter and you don't have to be afraid about corrections of which are much larger than the parameter itself. Also in the literature, more recently, there are several papers that have used a different name for this type of model, which is a slightly broken lepton number, because this small parameter breaks lepton number, and since it's a very small parameter, lepton number is broken, but only slightly. Okay, this is the idea. And well, the most popular model of this type is the inverse seesaw. So let me explain what this is about. We have again the right-handed neutrinos, okay, with the same quantum numbers as usual. And we add, let's say, a second type of fermion singlets that I call here X, which are also singlets of everything. Typically, you can add 3 families of right-handed neutrinos and 3 families of X. So you end up with 6 additional singlet states, but there are versions of this idea with less generations. So this 3 is just for replication of what you have in the standard model. And with these particles, you can write down the usual Yukawa coupling with the standard model lepton doublet and with the standard model Higgs doublet and the right-handed neutrinos. you can write a Dirac mass term between the right-handed neutrinos and the X fermions. And you can also write a Majorana mass term for the X fermions. Okay, and people say that this breaks lepton number. I will explain this in a while. In principle, you can also write a Majorana mass term for the right-handed neutrinos, like before, and you can call it mu r. Like this is mu x, so you can also have mu r. This is possible, but I don't have time to explain this in detail. If the hierarchy of scales that I'm going to assume later is produced, this parameter will always be subdominant in what concerns neutrino masses. So you can neglect it. It's not very important. Now, let me spend 1 minute clarifying something that I have read many times. And I know that people sometimes write this knowing what they mean. So they know what they want to express in this when they say this, but sometimes they don't. And I think this is important. So sometimes we say that a parameter breaks lepton number, but this is not very well defined. So let me explain this. So there are only two fields which have a very well defined lepton number. This is the lepton doublet and the charge lepton right-handed, the right-handed charge leptons. They have lepton number +1 because they are leptons. That's it. Okay. Any other field in your theory, we don't know a priori what is the lepton number of this field, because lepton number is not a symmetry that we have found in nature attached, for example, to a force, to an interaction. So you cannot define a lepton number for particles which are not leptons in principle. Now, a model conserves lepton number if you can find a lepton number assignment for the rest of the fields such that the Lagrangian is invariant under U1 transformations. For instance, in the standard model, you have this Yukawa term. So you have the lepton doublet, you have the lepton singlet, the charged leptons, and you have the Higgs doublet. This is -1 because you have the bar. This is +1. So if the Higgs boson, the Higgs doublet, has lepton number equal to 0, then this one conserves lepton number. And then you can claim that the standard model conserves lepton number. However, when there is no way in which you can assign lepton numbers, you try and you try and you try and you cannot find, and you actually prove that there is no way you can assign lepton numbers, then you say that lepton number is broken. And in that case, it is meaningless to say which parameter breaks lepton number, because what actually breaks lepton number is the presence, the simultaneous presence of all the parameters. Let me exemplify this with the inverse seesaw. So in the inverse seesaw, you can say that the lepton doublet has lepton number +1, as we said. The Higgs doublet has lepton number 0, as we found here for the lepton, the standard model coupling with the Higgs. But you don't know what is the lepton number of nu r, the right-handed neutrinos, and the lepton number of X. So you can say, for instance, let me try and assume that the lepton number of the right-handed neutrinos is 1 and the lepton number of X is 0. In that case, this term conserves lepton number. You can see it here. This term also conserves lepton number, but this one breaks lepton number. Okay, so this assignment doesn't work. Of course, it doesn't mean that this is the assignment that conserves lepton number. I just tried one of them. Now I say, okay, let me try with all, so the two new lepton numbers equal to 1. Then again, the first parameter conserves lepton number, the second conserves lepton number, and the third violates lepton number because you have +1 and +1. In that case, you would say that this is the parameter that breaks lepton number. But it is a matter of taste, if you want. It doesn't make any difference whether you assume that this is the parameter that breaks lepton number or this is the parameter that breaks lepton number. So this is one point that I wanted to emphasize, because sometimes you see in papers that this parameter breaks lepton number, and this is not correct. What breaks lepton number is the simultaneous presence of all the parameters, because you can always move the violation of lepton number from one parameter to the other just by reassigning lepton number at convenience. Okay. This was just a clarification that I wanted to make, that I think it's important in a school. Let me go back to the inverse seesaw. So now I have this chi multiplet, which includes, as before, the left-handed neutrinos, the right-handed neutrinos, and now also this X. In this case, the mass matrix now is bigger because we have 3 types of neutrinos, 3 types of fermions, and it looks like this. So we have these Dirac terms, these m's, which are the Dirac terms between the nu r and the x, and mu x is the Majorana mass for x. Now, if I assume that mu x is much smaller than this term, and this one is much smaller than m, you get, using exactly the same technique as we did for the type 1 seesaw, that the formula for the neutrino masses is given by this. Okay, so you get this more complicated combination of matrices that is proportional to mu x. This is very important. So you get something that looks like bev of the Higgs square divided by m times mu divided by m. Now, the whole point of this thing is that since mu is much smaller than m, you don't need m to be that large to get light neutrinos because you can play with the smallness of mu. For example, if now you want to have Yukawas of order 1 and you assume that mu is of the order of the electron volt, then capital M can be at the level of TeV, which is something that you can test, for example, at colliders at the LHC. So this is the great advantage of the inverse seesaw and all the low scale seesaws, that you can have at the same time large Yukawa couplings of order 1 and seesaw mediators, so new particles which are not that far from the electroweak scale. Also, incidentally, this is something that I also wanted to comment. The heavy fields, and this is important, their masses are given by capital M, and then they form quasi-Dirac pairs. So one of the guys is a bit heavier than M, and another one is a bit lighter than M, but they are very close in mass. And let me also point out that if mu x goes to 0, then these two guys are mass degenerate, they form an exact Dirac pair, and lepton number is restored because neutrino masses go to 0 as well. Okay, as I explained in a more generical way at the beginning. So in the inverse seesaw, you don't need a large scale. What you need is a small scale. This mu x is the one that is suppressing neutrino masses. And the advantage, as I said already, is that you have a very rich phenomenology. So you can have lepton pseudo-violation. I will discuss this in more detail tomorrow, because these particles that run in the loop are not that heavy anymore. And you can have also processes involving quarks. This is mutual conversion in nuclei. You modify the electronic current because you have new fermions that are not that heavy that mix with the normal neutrinos. And you can even look for these particles at the LHC, because some of these particles can be at the level of the TeV and then produced at colliders. So the phenomenology of these models is very rich. Let me now move to the second mechanism to suppress neutrino masses, which is radiative models. In radiative models, the idea is to have neutrino masses not produced at TeV level, but at some loop order. The idea in this case is to suppress neutrino masses, with this 16 pi square factor that appears for every loop. So the larger the loop order, the larger the suppression you will get for neutrino masses. There are many models of this type. Most of them appear at the one loop level, so one loop neutrino masses. But there are also models at 2 loop, at 3 loop, and even at 4 loop. But at 4 loop, as far as I know, there is only one that works, and it's not, well, it's a very special model. I won't say that it's a very typical model, but at least there is a model. At 3 loops, there are several models already. At 2 loops, there are a lot. And at 1 loop, there are many. The simplest radiative model is the C model that is already very old, from the 80s. Actually, this is a very impressive paper by C. And the model is very simple. So you just add a second Higgs doublet. This phi2 is a second Higgs doublet with exactly the same quantum numbers as the standard model Higgs doublet, and a singly charged scalar, nothing else. So this scalar is singlet under ratio 3, singlet under ratio 2, and has hypercharge +1. So the electric charge of this guy is +1 as well. Thanks to this guy, you can have a coupling of this type. You can see that the gate symmetry is perfectly conserved in this Yukawa coupling. So you have 2 doublets, 1 singlet, and hypercharge is also 0 in this coupling. Finally, there is also a cubic term in the scalar potential involving the typical Higgs doublet, the second Higgs doublet that we have introduced, and the singly charged scalar. And as usual, you have the normal Yukawa coupling with the Higgs doublet, at the charged leptons. And you get neutrino masses by loops at this, as you can see here. So this coupling here is what I call here F. This is F. This coupling here is the standard model Yukawa coupling. And this coupling here is the cubic term that you have in the scalar potential. This is already enough to produce Majorana neutrino masses, this simple model. And it is very interesting that you have neutrino masses already at the one loop order without adding any fermion. You just add scalars. So this is a very interesting model for its economicality, and also because it shows that the standard model scalar sector is actually very simple, very economical. As soon as you introduce a few additional scalars, you break lepton number, you induce Majorana mass 10 for the neutrinos. A second example of this model, or this type of models, is the so-called Sibabu model, which, by the way, this model is called typically Sibabu because it was introduced independently by C in a paper in 1986 and by Babu in a paper in 1988. But it is funny because Cheng and Lee introduced it already in a paper in 1980, and nobody calls it Cheng and Lee model. So I think, to be fair, we should call it the Cheng, Lee, C-Babu model to be fair with the authors. Anyway, in this case, also, you don't add additional fermions, but you just add scalars. So you have a singly charged scalar and a doubly charged scalar, and thanks to that, you can draw this diagram here, which now induce neutrino masses at two loops, not one, but two loops. Another model that is very popular, and I wanted to mention very briefly, is the so-called scotogenic model. Skotos is a word that comes from Greek and means darkness, and you will see in a second why this is the name of the model. Now, in addition to the standard model gate symmetry, you add an additional Z2 symmetry. You remember that we did this yesterday in a model as well. And under this symmetry, all the particles in the standard model are even, so they are plus. But the new particles that I will add, this N and this eta, will be minus. So they will be odd under this symmetry. N is just, as you can see, a singlet, a fermion singlet, like the right-handed neutrinos in the models that I discussed before. And eta is a second Higgs doublet, but with a minus sign here. So the normal Higgs doublet would be plus, and eta is minus. Since this is minus and this is minus, you can write down this Yukawa coupling. So this is the equivalent of the normal coupling between the lepton doublet, the Higgs doublet, that is not the Higgs anymore, but this eta, and this fermion singlet. You can see that you cannot write down this coupling with the normal Higgs doublet because of the Z2, because this is plus, minus, minus, and this is okay. But if you had here the Higgs doublet, this would be plus, plus, minus, that is forbidden. That's why you don't have a Yukawa coupling with the Higgs. Because of that, neutrinos do not get masses at two levels. This is the point of this Z2 symmetry. Now, you can also have Majorana masses for the N fermions, and there is a very important coupling in the scalar potential, a quartic coupling that is called typically lambda 5, between the standard model Higgs doublet and eta, okay, that is given here. And you can get neutrino masses at the one loop level, as you can see in this diagram. And now, why people call this scotogenic, and what is the relation to darkness? The point is that the lightest particle that is charged under the Z2 symmetry will be completely stable, because the Z2 symmetry is assumed to be completely conserved in the model. Because of that, since you have a particle that is stable, if it has the good properties, it could be the dark matter particle that fills the universe. So this model not only gives you neutrino masses, but also gives you a dark matter candidate. And this is why people like this model a lot, because with very few ingredients, you solve two problems, neutrino masses and dark matter. And well, relative models also have a very good phenomenology, because thanks to this suppression due to the loops, to the loop factor, you can make the mediators, the new particles, much lighter. For example, in the Sibabu model, you can have lepton flavor violation. So a process like this taking place at tree level. So a process in which you violate lepton flavor at tree level, and therefore this could be completely visible in experiments. Also in the scotogenic model, you can have processes like this at the one loop level. Also, you have phenomenology associated to the fact that you have a dark matter candidate. And I could give you many other examples. Now, let me move. I don't know how well I'm doing with time. Let me know if I'm if I'm reaching the end of the lecture, because I'm not paying attention to the time. Let me move to models that induce neutrino masses with dimension larger than 5 operators. The idea, again, is to suppress neutrino masses as much as possible in such a way that lambda does not need to be that large. That way you can have masses for the new particles at lower scales. So in this case, you have the usual factor, this bev squared divided by lambda, and you have some additional factor depending on the dimensionality of the operator that will give you a suppression, because lambda is larger than the bev of the Higgs. So as you probably remember from yesterday, and I repeated today, the Weinberg operator is the lowest dimensional operator. It appears at dimension 5 that leads to neutrino masses that breaks lepton number into units and appears at dimension 5. But there are additional operators that appear at dimension 7, dimension 9. All dimensions actually have operators that break lepton number into units, and even in different units, but in particular in 2 units. So for example, at dimension 7, you have this operator. You have the usual Weinberg operator times phi dagger phi. Okay, this is dimension 7 because you have the 5 dimensions included in the Weinberg operator plus 2 dimensions coming from phi dagger phi. So in this case, this would induce neutrino masses proportional to the bev square divided by lambda coming from the Weinberg operator times bev square divided by lambda square coming from the additional phi dagger phi. Okay, so
yes, you have 10 minutes.
Perfect. Thank you, Carlos. That is very nice. Okay, so you can generalize this idea to any dimensionality. If instead of phi dagger phi to the 1, you have it to d minus 5 divided by 2, eventually you reach this expression for the factor that you get from neutrino masses, okay, which is also given here. So this is the idea. If you have a model that does not realize the Weinberg operator, but realizes one of these operators of higher dimensionality, then automatically you have a suppression by lambda that is not 1 over lambda, but 1 over lambda to some additional power. So if this is the case, you don't need lambda to be that large because the suppression is more powerful in this case. This is the idea. However, this is not easy in practice. The reason is that typically when you have a model that induces one of these operators, it also induces the Weinberg operator. So you have to ensure that the Weinberg operator is not the dominant contribution to neutrino masses. This can be done with symmetries, with additional symmetries, but it's tricky. It's not so simple. And actually there are very few models that actually do this. I will show you an example. I will show you an example that induces neutrino masses with a dimension 9 operator. Okay, this is given by this paper by Kumerichi et al. 2012. And the model is not simple because it has to introduce a fermion and a scalar with a representation that is a bit exotic. So F is a singlet of SU3, but it's a 5-plet of SU2. I'm confident that you are not, most of you are not familiar with a 5-plet of SU2. This is not a very common representation, but it's a possible representation. It's legal, completely legal. And S is not a tablet, is not a singlet, but it's a 4-plet of SU2. Okay, so again, a very exotic representation. Now, what is the idea behind this? The idea is that since this guy is a 5-plet, you cannot couple it to the Yukawa, to the standard model Yukawa with the lepton doublet and with the Higgs doublet, because SU2 left would be broken. So a coupling of this type that I write here, if this is, instead of S, you have the standard model Higgs, this is forbidden due to the SU2 left symmetry. So you cannot write it down. You need S to make this coupling invariant under SU2, gauge invariant. Why is that important? Because S does not get a bev. Okay, well, actually it does get a bev, sorry, but the bev of S is connected to the bev of phi thanks to these couplings in the standard model Lagrange. In the standard model, sorry, in the scalar potential. In the scalar potential. So let me show you how this works with a diagram. So this is the diagram that leads to neutrino masses in this model. So you have the Yukawa coupling that I mentioned already with F and S. And now the BEF of this scalar is induced by this coupling, this quartic coupling with three Higgses. Okay, so this is one of the couplings that I mentioned here. So you have Higgs, 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 S. Okay, so this is lambda 4. This coupling here. And you need it twice because you need the Yukawa to take place twice. So now if you count, you have 1, 2, 3, 4, 5, and 6 Higgses. So in the end, you have an operator of this type. So this is a dimension 9 operator. Okay, if you integrate out S and F, you end up with a dimension 9 operator. You don't induce the Weinberg operator, but you induce this dimension 9 operator. Then thanks to that, you get a formula for neutrino masses, which is basically Yukawa square. You have the Yukawa here and here, lambda 4 square. You have lambda 4 here, lambda 4 here. Then 6 Higgs BEFs. You can see immediately that they come from these Higgses. And then in order to make these dimensions correct, you need 5 powers of m, as expected from a dimension 9 operator. So this is the model, and this is how it works. However, there is a little problem. In this model, you also induce a scotogenic-like dimension 5 contribution. So you can also write down, you find that basically you can close this, you can connect these scalar lines and close the loop, and you get this particular diagram that, as you remember, was discussed already when we discussed the scotogenic model. So what is the trick that people do when they discuss this model? They assume that this coupling here, which is lambda 5, it's defined here, this coupling, this lambda 5, is very, 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 very small. If this is very, 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 very small, then this is not dominant and this is dominant. This is the one, and this is the idea behind the model, that this is actually the dominant contribution to neutrino masses. So as I said, building models that induce neutrino masses with dimension larger than 5 operators is possible, but typically you need to assume that the contributions to lower dimensional operators are suppressed by some reason, either symmetries or you have a small coupling like in this case. So they are not that simple to construct. Now, since I have still 5 minutes, let me comment on a couple of things that I didn't discuss so far. The first one is that I've been discussing all the time in this lecture Majorana neutrino masses and models in which lepton number is broken into units explicitly. So I have always a parameter in the Lagrangian, or as I said before, a combination of parameters that break lepton number explicitly. However, you can also do the same game with a spontaneous lepton number violation. So you can start with a Lagrangian that conserves lepton number, then some scalar gets a BEF, scalar that has lepton number, then you break the lepton number symmetry, and then you have Majorana neutrino masses spontaneously. And basically, it works essentially as we have discussed already. There are very few differences. There is only one that I will mention later. So, for instance, let's suppose we consider the type 1 seesaw, the typical model that everyone has in mind for neutrino masses. But now we impose that we want to have conserved lepton number. If we want to have conserved lepton number, the Majorana mass for the right-handed neutrinos is forbidden. But let me add a scalar with lepton number equal -2. Then, in that case, I can write this Yukawa coupling. I can have a Yukawa coupling that I call F that couples two right-handed neutrinos to sigma in this particular way. So this is now lepton number conserving because you have +1, and this is -2. So everything is fine. We are happy. Lepton number is conserved. What is the trick? That sigma will have a BEF, and when sigma gets a BEF, lepton number will be broken into units, and a Majorana mass 10 for new R will be induced. The Majorana mass 10 that appears in the formula of the seesaw. So you will get neutrino masses exactly as in the seesaw, as in the type 1 seesaw. What is the difference with explicit lepton number violation? The difference is that in this case, this model contains additional degrees of freedom because you have sigma. Sigma contains a real part and an imaginary part. And this is very important because the imaginary part of this scalar actually is a Goldstone boson. You know that there is something very important in quantum field theory that is called the Goldstone theorem, every time you have a continuous global symmetry, like in this case, a U1 symmetry, U1 lepton number, that is spontaneously broken, your theory will contain massless Goldstone bosons. This is the case in this model. So you have, in this theory, you will have, and you can calculate it explicitly, you can construct the whole scalar potential, and you can calculate the mass for the imaginary component of sigma, and you can easily find that the mass is 0, exactly 0. This particle is usually called the majoron because it's the particle associated to the fact that you have Majorana neutrinos. So the majoron is the Goldstone boson associated to the breaking of lepton number in 2 units. Why is this important? Because, well, having a particle with 0 mass, exactly 0 in your theory, affects the phenomenology dramatically. And there are very important constraints that you have to fulfill for this to be viable, phenomenologically viable. I don't have time to discuss this, but this is something that I think you should know, that this is in principle possible. You can also violate the lepton number spontaneously, but there is this difference, the Goldstone boson, the major. And now, and this is just a brief comment, usually in many models, you combine suppressions. So I made this division between suppression mechanism 1, suppression mechanism 2, suppression mechanism 3. But in practice, what people do in many models is to combine more than one suppression mechanism. For example, in the scotogenic model, I mentioned that this is a one-loop model, so you have the suppression mechanism coming from the loop. But in practice, what people do is they assume that this coupling here is also very small. So you combine the suppression mechanism from the loop with the, this epsilon parameter that I mentioned, this first suppression mechanism, a small violation of lepton number. So that allows you to increase, as usual, the Yukawa couplings and to reduce the mass of the mediators. So this is a way to combine two suppression mechanisms. And with this, I conclude. So I gave you more or less broad overview of Majorana neutrino masses. There are many models in the market, really many. I just mentioned a few of them, maybe the most popular ones, but there are many more. And I'm pretty sure many of the models that I discussed are known by you already. For example, yesterday, Alexis Plasencia discussed the inverse seesaw in his talk, very nice talk. And some of them maybe are new, but I can promise there are many more. Okay, this is just a broad overview. And before I conclude, again, exercises like yesterday for those who are interested and want to practice a little bit. This time I have two. I mentioned in my lecture that there are models that are known in the literature up to dimension, up to loop order 4. So neutrino mass is induced at the 4 loop order, but there is no model at 5 loops. So is it possible to construct a realistic model that generates neutrino masses at the 5 loop order? So this is the first exercise for you to think a little bit. And the second, and this is very well connected to Jose Ignacio Illana's lectures. So I mentioned in passing very quickly that there is a version of the seesaw that uses a scalar triplet. If the scalar triplet has a V, it modifies something that is called the rho parameter. It's a very important quantity in the standard model. And it's the relation between the W boson mass and the Z boson mass times theta width. So what I ask you to do is to calculate what is the rho parameter in the presence of delta when delta gets a V. And you should find that it deviates from 1. It's not 1 anymore. So what is the value that you can have of this VEF if you want rho to be to deviate from 1 not more than 10 to the minus 3? Okay. This is an interesting exercise that probably Jose Ignacio will also discuss or mention something similar in his lectures that I really look forward to because they will be very nice lectures. That's what I wanted to say. So thank you very much for your attention. And if you have questions or comments, they are welcome.
Thank you very much, Avelino. We have time for a quick question.
I have one question.
Okay.
Thank you very much, Avelino, again for your very nice explanation. This is a very subjective question. I want to ask you if you want a favorite model and why.
That's a good question. It's hard to answer. On one side, I like the type 1 seesaw because it's very simple and it fits very well in grand unification. So I think everybody believes that this is a very simple way to get neutrino masses, but it's impossible to test directly. So if I can choose two favorite models, one would be the type 1 seesaw because it's simple and we all like it. And a second variation would be the scotogenic model. The scotogenic model is also a model that I like a lot because it also gives you dark matter. And it's not that complicated. It's a very simple model as well.
Thank you.
Thank you.
I think that Carlos lost connection for a while. Carlos, we can barely hear you. So maybe I can just ask my short question. Yes. So apart from the Hydron, in other cases where scalar appears, it can be in principle problematic if its mass is not close to the highest dynamical scale. Can you comment on that?
Yes. This is important. Yes, you are right. So yeah, you need to engineer a little bit the scalar potential to avoid having a very light scalar. And in some cases, this is problematic. This is true. But well, typically you have sufficient parameters to play with. And in the end, you typically can make some of the scalars as heavy as you need. By heavy, typically you need a few hundred GeV to be fine.
Okay, thank you very much again.
Thank you, Pablo.
Gabriel, please.
Hola, Avelino.
Hola.
I have a question only if students don't want to ask.
Go ahead, please.
Okay, thank you. I have also a naive question, but please be merciful with me with your answer. We want to generate the mass of the neutrinos because we don't like a very small Yukawa coupling. Yes. Mm-hmm. In the way we have to a bonus of extra particles in any mechanism you have discussed today. Mm-hmm. What is the most promising test of those additional particles that in order not to have an ad hoc solution to the small Yukawa couplings?
Yes.
And at the same time, let me say why we should worry about 10 to the minus 12 for the Yukawa coupling and not 10 to the minus 6.
That's a perfectly fine question, and it makes a lot of sense. So I completely agree with you that we already have a coupling that is 10 to the minus 6, so why not 10 to the minus 12? So it's fine, no? Already, when you accept 10 to the minus 6, you can accept 10 to minus 12. The problem is that it's more, it's aesthetical on one side, but aesthetical doesn't mean a lot. I agree with that. But it's also practical. So with such small couplings, you cannot test the model. There is no way you can test the model because there is no effect that you can detect that can be associated to that coupling if the coupling is that small. So if you want, you can see it in a different way. You can think that we are discussing other versions, other models that give masses to neutrinos to convince ourselves that that simple solution is the one that is chosen by nature. Because there is no way we can confirm that solution. We can only rule out other possibilities. This is my point of view, that that possibility is of course possible, it's fine, but you cannot test it. So let's test other possibilities and rule them out. And that way we can gain confidence on that one. And you also asked me about ways to distinguish experimental tests of these different models. So that depends on the model, of course. In most of the models, the best way to test the model is to produce the particles, for example, at a collider, because then you can measure the couplings, you can measure the mass, etc. This is not always the case. And then I will discuss in the third lecture tomorrow some indirect ways which are related to lepton flavor violation. So in most of these models, you can have observable lepton flavor violation, and sometimes you have predictions. So even though they are not direct, and then it's not so easy to say this is the model, at least you can say something. You can learn a lot about what is the possible model that is behind.
Okay.
Was it okay, the answer? Or maybe I discussed a lot of things that were not related to your question.
No, it's okay. It's okay. Actually, it was what I expected.
Thanks, Gabriel.
Carlos, can you go on?
I think we should stop here now.
Carlos, I'm sorry. Again, we can almost hear you. So, I mean, I'm sure Carlos is saying we have to cut the discussion now. And now the breakout rooms will be open. So please join your favorite one. And it is important to emphasize that the parallel session will last exactly 2 hours at most. So we should be seeing here again at, let's say, 5 minutes plus 11, okay? So can anyone open the parallel sessions, the breakout rooms, please, so that we join them?
Pablo, ¿estás ahí?
Sí, lo que pasa es que solo veo una sala y no tiene nombre, entonces...
Se están generando, Pablo, un minutito, por favor, de
Esperemos,
paciencia.
esperemos. Sí, esperemos. ¿Pero tienes algún problema técnico, Gerardo, o era eso?
No, era eso.
Ok, gracias.
Are the breakout rooms open, Pablo? I don't see them.
Not yet, as far as I can see. Maybe there is some technical problem.
Okay.
Let's wait a bit, please. Of course, it is 2 hours since the moment we can start the parallel sessions. So we have some delay, then we can finish a bit later.
The rooms are now generated, huh?
Yes, thank you, Alfredo. I could already join one. I confirm. Thank you.
Okay, very good.